Right now, 8 billion human hearts are beating on a single rock, spinning through an endless void. But here's what will make you question everything you think you know. Every beat of your heart, every thought in your mind, every atom in your body came from this. Something smaller than the period at the end of this sentence contained everything that would ever exist. Your morning coffee, Shakespeare's sonnets, the love you feel for someone, the fear that keeps you awake at night. All of it, every human emotion, every sunset, every star, compressed into a space so impossibly tiny it makes a grain of sand look like a universe. That's the question that will haunt you, because the answer, the real answer, is so beautiful and so terrifying that once you hear it, you'll never look at anything the same way again. You think you're watching a documentary about space. You're wrong. You're about to discover that you are space. You are time. You are the universe looking back at itself through your own eyes, trying to remember how it was born. And this story, this impossible, magnificent, terrifying story, begins with the most dangerous question ever asked. What if everything you've ever been told about reality is wrong? Chapter 1. The moment everything began. You're holding a grain of sand between your fingers. Now imagine squeezing all the matter in the observable universe, every star, every planet, every atom that makes up you and me, into a space far smaller than that grain of sand. In fact, smaller than an atom, smaller than anything we can meaningfully measure. This isn't science fiction. This was reality 13.8 billion years ago, and from this impossibly tiny point, everything you see, everything you are, and everything that has ever existed exploded into being in the most spectacular event in the history of existence. We call it the Big Bang, but that name barely captures the profound mystery we're about to explore together. Before we dive into what happened, let's confront the question that keeps physicists awake at night. How can something come from nothing? It sounds absurd, doesn't it? After all, everything in our daily experience tells us that things don't just pop into existence. Your coffee cup doesn't materialize out of thin air. Buildings don't spontaneously assemble themselves from empty space, but here's where our intuition fails us completely. The universe doesn't play by the rules we're familiar with, especially when we're talking about the very beginning of everything. You see, when we say the universe came from nothing, we're not talking about the kind of nothing you find in an empty room or the vacuum of space. We're talking about the absence of space itself, the absence of time itself. Before the Big Bang, there was no before, because time hadn't been invented yet. Think of it this way. Imagine asking what's north of the North Pole. The question itself becomes meaningless because north is a direction that only makes sense once you have the framework of the Earth's surface. Similarly, asking what came before the Big Bang is like asking what's north of north. It's a question that dissolves once you understand that time itself was created in that first moment. But this raises an even deeper mystery. If there was no time, no space, no matter, no energy, then how did anything begin? The answer, as unsatisfying as it might seem, is that we're asking the wrong question. The universe didn't begin in time and space. The universe is the beginning of time and space. Reality didn't happen somewhere. Reality created somewhere as it happened. Modern quantum mechanics gives us tantalizing clues about how this might work. At the quantum level, particles actually do pop in and out of existence all the time. Virtual particles appear from apparent nothingness, exist for impossibly brief moments, then vanish again. It's not magic. It's the fundamental nature of reality at its smallest scales. Perhaps the entire universe is simply the ultimate quantum fluctuation, a cosmic virtual particle that happened to keep existing instead of vanishing back into the void. But even this explanation leaves us with profound questions that push against the very limits of human understanding. What happened in the first fraction of a second after the universe began makes every action movie explosion look like a gentle breeze. We're talking about a period of time so brief that light, the fastest thing in the universe, could barely travel the width of an atomic nucleus. Yet, in this incomprehensibly short moment, the universe underwent the most dramatic transformation in its entire history. Let's put ourselves there in that first instant. The temperature is beyond anything we can truly comprehend, billions of times hotter than the core of the sun. Matter as we know it cannot exist. Even atoms cannot form. The universe is a seething cauldron of pure energy, so dense and hot that the very forces that govern reality are unified into a single primordial power. Then, in less time than it takes for light to cross the space occupied by a proton, something extraordinary happens. The universe inflates, not gradually, not slowly. It doubles in size, then doubles again, then again, billions upon billions of times in a period we call cosmic inflation. In less than a trillionth of a trillionth of a trillionth of a second, a region of space smaller than a proton expands to the size of a grapefruit. This sounds impossible, and by the standards of our everyday experience, it is. Nothing can travel faster than light, Einstein taught us. But here's the cosmic loophole. Space itself can expand faster than light. The galaxies aren't racing through space at impossible speeds. Space itself is stretching, carrying them along like raisins in an expanding loaf of bread. As the universe inflates and begins to cool, something profound happens. The single unified force that governed everything begins to crack apart, like ice splitting under pressure. First, gravity separates out, becoming the weakest but most far-reaching of nature's forces. Then, the strong nuclear force that holds atomic nuclei together splits off. Finally, the electromagnetic force and the weak nuclear force differentiate from each other. It's as if the universe has just separated into the four fundamental languages it will use to write the story of everything that comes next. Gravity to shape the large-scale architecture of space and time, electromagnetism to bind atoms and create light, the strong force to forge the nuclei of atoms, and the weak force to power the nuclear reactions that will make stars shine. By the time this cosmic symphony of creation has played its opening notes, the universe is already 1,000,000 billion times larger than when it started. And it's still growing. But the most remarkable chapter is yet to come. If the first fraction of a second was about setting the stage, the next 3 minutes were about creating the raw materials for everything that would follow. This is the era cosmologists call Big Bang nuclear synthesis, the universe's first and most important chemistry lesson. Picture the universe now. It's been expanding and cooling for about 1 second. The temperature has dropped to a mere 10 billion degrees Celsius, still far too hot for atoms to form, but cool enough for protons and neutrons to exist without immediately being torn apart by the cosmic furnace around them. This is when the universe becomes a nuclear reactor on an unimaginable scale. Protons, the nuclei of hydrogen atoms, begin colliding with enough force to overcome their mutual electric repulsion and stick together. When a proton captures a neutron, it becomes deuterium, heavy hydrogen. Capture another neutron and you get tritium. But the real prize comes when deuterium nuclei crash into each other and fuse, creating helium-4, the second element on the periodic table. For exactly 17 minutes and 46 seconds, the entire universe is the perfect temperature and density for this cosmic alchemy. Not too hot, or the newly formed nuclei would be immediately blasted apart. Not too cool, or the particles wouldn't have enough energy to fuse in the first place. It's a Goldilocks moment on a universal scale. Everything has to be just right. And just right it was. In those precious few minutes, the universe transforms roughly 25% of all protons into helium nuclei. It also creates trace amounts of lithium, the third element, but then, as quickly as it began, the nuclear furnace shuts down. The universe has expanded and cooled past the critical threshold. The temperature drops below 1 billion degrees and nuclear fusion grinds to a halt. This is one of the most profound moments in cosmic history, though it might not seem like it. The universe has just determined the basic composition of all ordinary matter for the rest of time. 3/4 hydrogen, 1/4 helium, with just a trace of lithium. For the next several 100 million years, these will be the only elements that exist. No carbon, no oxygen, no silicon, no iron, none of the heavy elements that make planets and life possible. That cosmic recipe, 75% hydrogen, 25% helium, is still with us today. Look up at the sun, and you're seeing a ball of gas that's still primarily composed of the elements forged in those first 3 minutes of creation. The hydrogen in every molecule of water you've ever drunk was born in that primordial nuclear furnace. You are intimately connected to that moment when the universe first learned to transform energy into matter. But here's what makes this story even more remarkable. We can still see the afterglow of those first moments. Imagine you could take a photograph of a newborn baby and then decades later still see that photo glowing faintly in the air around you. That's essentially what happened with the universe, and it's one of the most beautiful discoveries in the history of science. For the first 380,000 years after the Big Bang, the universe was opaque. Not dark, it was blazing with light. But that light couldn't travel very far because it was trapped, constantly bouncing off free electrons like a flashlight beam trying to penetrate a thick fog. The universe was like the interior of a star, blindingly bright but impossible to see through. Then something magical happened. The universe had cooled enough to about 3,000 degrees Celsius that electrons could finally settle down with protons to form the first complete atoms. This moment is called recombination, and it changed everything. Suddenly, with the electrons bound up in atoms, light could travel freely for the first time. The cosmic fog lifted and the universe became transparent. The light that was released at that moment, the first light that could travel freely through space, is still traveling. And here's the astounding part. We can still see it. That ancient light, stretched and redshifted by 13.8 billion years of cosmic expansion, now comes to us as microwave radiation. We call it the cosmic microwave background, or CMB, and it's literally a baby photo of the universe. This discovery happened almost by accident. In 1965, 2 engineers at Bell Labs, Arno Penzias and Robert Wilson, were trying to track down an annoying source of static in their radio antenna. No matter where they pointed their equipment, they detected the same faint microwave hiss. They cleaned bird droppings off their antenna, thinking that might be the problem. The noise remained. What they had stumbled upon, without knowing it, was the echo of creation itself. This cosmic background radiation is remarkably uniform, the same temperature in every direction to within 1 part in 100,000. But it's not perfectly smooth. There are tiny fluctuations, regions that are slightly warmer and slightly cooler than the average. These minute variations are incredibly important because they represent the seeds of everything we see today. The slightly denser regions would eventually grow under the pull of gravity into the first stars and galaxies. Think of it this way. Those tiny ripples in the cosmic microwave background are like the initial imperfections in a ball of dough that determine where the air bubbles will form when it rises. Except in this case, the bubbles became the vast cosmic web of galaxies and galaxy clusters that fills our universe today. When we map the cosmic microwave background with incredible precision, as missions like WMAP and Planck have done, we're essentially looking at the blueprint of everything. We can see in those ancient light patterns the fingerprints of cosmic inflation, the ratio of ordinary matter to dark matter, and even clues about the fundamental geometry of space itself. But perhaps most remarkably, this discovery gives us absolute confidence in our understanding of the Big Bang. The cosmic microwave background was predicted by theory decades before it was observed. The fact that we found exactly what the Big Bang model said we should find, right down to the precise temperature and the tiny fluctuations, is one of the greatest triumphs in the history of science. We're literally bathed in the afterglow of creation. Every second of every day, billions of these ancient photons, messengers from the universe's infancy, are streaming through your body. You are constantly being touched by light that began its journey when the universe was young and transparent and full of infinite possibility. So there you have it, the moment everything began. From a quantum fluctuation smaller than the smallest particle we can imagine, the universe inflated, cooled, and began the long process of creating the complexity we see today. In those first 3 minutes, it forged the elements that would later become stars and planets. And it left us a message, written in light itself, that we can still read today. But here's what's truly mind-bending. All of this spectacular creativity, all of this cosmic genesis, represents only about 5% of what actually exists. The atoms forged in those first minutes, the matter that makes up every star, every planet, and every one of us, is apparently just a thin frosting on a much larger and far stranger cosmic cake. What fills the other 95% of the universe? What is the invisible architecture that holds everything together and drives the expansion that began with the Big Bang? The answer will challenge everything you think you know about the nature of reality itself. Chapter 2. The Dark Architecture. Imagine you're an architect tasked with building the most magnificent cathedral ever conceived. You have your blueprints, your vision is crystal clear, but there's just one problem. 95% of your building materials are completely invisible. You can't see them, touch them, or even detect them directly. Yet somehow you must trust that they're there, holding up the walls, supporting the roof, creating the very structure that makes your cathedral possible. This isn't a thought experiment. This is the reality of our universe. Everything you can see, every star that twinkles in the night sky, every galaxy spiraling through space, every planet, every grain of cosmic dust, represents just 5% of everything that exists. The other 95%, it's made of substances so mysterious, so alien to our everyday experience that we call them simply dark matter and dark energy. And without them, nothing you see would exist. The story begins in the 1930s with a Swiss astronomer named Fritz Zwicky, who was studying a cluster of galaxies called Coma. What he discovered should have been impossible. These galaxies were moving so fast that they should have been flung apart long ago, scattered across the cosmos like marbles rolling off a tilted table. Yet there they were, held together in a gravitational embrace that defied explanation. Zwicky calculated the total mass of all the visible stars and gas in the cluster. Then he calculated how much mass would be needed to generate enough gravity to keep these speeding galaxies bound together. The numbers didn't match, not even close. To hold the cluster together, there had to be 6 times more matter than anyone could see. But where was it hiding? For decades, astronomers assumed they were simply missing something obvious. Perhaps clouds of gas too cool to detect, or swarms of dim brown dwarf stars lurking in the darkness between galaxies. They called this missing matter dark, not because it was sinister, but because it seemed to emit no light. Then, in the 1970s, astronomer Vera Rubin made an observation that changed everything. She was studying the rotation of spiral galaxies, measuring how fast stars moved at different distances from their galactic centers. According to everything we knew about physics, stars on the outer edges of galaxies should move more slowly than those near the center. Just like planets in our solar system, Mercury races around the Sun much faster than distant Neptune. But that's not what Rubin found. The outer stars were moving just as fast as the inner ones, sometimes even faster. It was as if the planets in our solar system all orbited the Sun at exactly the same speed from Mercury to Neptune. Impossible unless there was far more mass in these galaxies than anyone could see. Galaxy after galaxy showed the same pattern. The visible matter, the bright stars and glowing gas clouds, was just the tip of an enormous gravitational iceberg. Hidden beneath the surface was 5 times more matter, invisible and undetectable by any telescope ever built. This wasn't just missing stars or hidden gas. This was something fundamentally different from anything we'd ever encountered. Something that had gravity but gave off no light. Something that shaped the very architecture of the cosmos while remaining completely invisible to human eyes. Scientists began calling it dark matter, and with that name came a humbling realization. We were living in a universe where the vast majority of matter was made of something we couldn't see, couldn't touch, and couldn't understand. It was as if we'd spent centuries studying the ocean while only noticing the whitecaps on the waves, completely missing the vast depths beneath. But dark matter was just the beginning of the mystery. As astronomers peered deeper into space and further back in time, they discovered something even more unsettling lurking in the cosmic shadows. In 1998, 2 teams of astronomers set out to measure something they thought they already knew: how fast the expansion of the universe was slowing down. Everyone agreed that the universe was expanding. Edwin Hubble had proven that in the 1920s. But gravity, they reasoned, must be gradually putting on the brakes, slowing that expansion over cosmic time. They chose exploding stars called Type Ia supernovae as their cosmic measuring sticks. These stellar explosions are remarkably consistent. Each one releases almost exactly the same amount of energy, making them perfect standard candles for measuring distances across the universe. By comparing how bright these supernovae appeared to how bright they should be, astronomers could calculate exactly how far away they were. And by measuring their redshift, how much their light was stretched by the expansion of space, they could determine how fast the universe was expanding at different points in its history. What they found shattered our understanding of cosmic evolution. The universe wasn't slowing down, it was speeding up. Imagine throwing a ball into the air and watching it accelerate upward instead of falling back down. That's essentially what these astronomers observed on a cosmic scale. Not only was the universe expanding, but that expansion was getting faster and faster with each passing moment. This discovery earned them the Nobel Prize in Physics, but it also confronted humanity with perhaps the deepest mystery in all of science. What force could be powerful enough to accelerate the expansion of the entire universe? What could overcome the gravitational pull of hundreds of billions of galaxies and drive them apart at ever-increasing speeds? Scientists named this mysterious force dark energy, and the numbers were staggering. To account for the accelerating expansion, dark energy would have to make up about 70% of everything in the universe. Combined with dark matter's 25%, that left just 5% for all the ordinary matter we can see, every star, planet, gas cloud, and living creature that has ever existed. We weren't just missing most of the matter in the universe, we were missing most of reality itself. Dark energy behaves unlike anything in our everyday experience. While matter and energy become more diluted as space expands, imagine dots on a balloon becoming farther apart as you inflate it. Dark energy maintains constant density even as the universe grows. As space expands, more dark energy appears to fill the new volume, driving the expansion faster and faster in a runaway process that defies our intuition about how the universe should work. Some physicists propose that dark energy might be the energy of empty space itself, the quantum vacuum seething with virtual particles that pop in and out of existence. Others suggested it might be a new field pervading all of space, slowly rolling down an energy hill like a ball on an invisible slope. Still, others wondered if our understanding of gravity itself might be incomplete, requiring new physics to explain what we were seeing. But whatever dark energy is, it's writing the ultimate destiny of our universe. And to understand how it's doing that, we need to see the cosmic architecture it's helping to build, a vast web of matter that spans billions of light years. If you could step outside our galaxy and view the universe from the ultimate vantage point, suspended in space with the power to see across billions of light years, you would witness one of the most beautiful and intricate structures ever discovered. The cosmic web, a magnificent scaffolding of dark matter that spans the entire observable universe. Picture the most elaborate spider web you've ever seen, but one that extends not across a garden corner, but across billions of light-years of space. Along its strands, like dewdrops catching the morning light, hang clusters and superclusters of galaxies, vast cities of stars connected by highways of dark matter that stretch across the cosmic void. This web began forming in the earliest moments after the Big Bang, when the universe was still smooth and featureless. Tiny quantum fluctuations, random variations in density no larger than subatomic particles, were stretched to cosmic proportions by the rapid expansion of space. These microscopic ripples became the seeds around which all future structure would grow. Dark matter, immune to the radiation that kept ordinary matter hot and dispersed, began collapsing under its own gravity first. It formed an invisible framework like the steel skeleton of a skyscraper under construction. Only later, hundreds of thousands of years after the Big Bang, would ordinary matter cool enough to fall into the gravitational wells that dark matter had already carved in space-time. The result is a universe organized on the grandest possible scale. Massive filaments of dark matter, hundreds of millions of light-years long, connect dense nodes where thousands of galaxies cluster together. Between these filaments stretch vast cosmic voids, regions so empty that a traveler could journey for hundreds of millions of light-years without encountering a single galaxy. Our own local group, containing the Milky Way, Andromeda, and dozens of smaller galaxies, sits on one of these cosmic filaments. We're part of the Laniakea supercluster, a structure so vast that light takes 500 million years to cross from one end to the other, and Laniakea itself is just one branch in the cosmic web, connected to other superclusters by an intricate network of dark matter streams. Computer simulations reveal this web in stunning detail. Scientists can model how dark matter flows through space, how it clumps and condenses, how it channels ordinary matter into the patterns we observe today. These simulations show dark matter streaming along the web's filaments like water flowing through a vast irrigation system, carrying with it the gas and dust that will eventually form new stars and galaxies. But the cosmic web is not static. It's growing, evolving, responding to the mysterious force of dark energy. As space expands and dark energy becomes more dominant, the web is being stretched and distorted, the connections between galaxy clusters are weakening, the voids are growing larger and emptier. In a sense, we're witnessing a cosmic tug-of-war. Gravity and dark matter try to pull structure together to build denser concentrations of galaxies and stars. Dark energy works in opposition, driving space apart, weakening the connections in the cosmic web, and ultimately determining whether the universe will continue building complexity or slide toward cold, empty isolation. This battle between construction and dissolution is shaping not just the large-scale structure of the universe, but the very possibility of life itself. And to understand why, we need to examine how this invisible architecture influences the formation and evolution of galaxies, including the one we call home. Every galaxy in the universe, including our own Milky Way, is embedded within a massive halo of dark matter, an invisible sphere of mysterious particles that extends far beyond the visible edge of the galaxy and contains 5 times more mass than all the stars, gas and planets combined. Think of a galaxy not as an isolated island of stars, but as the bright center of a vast, dark matter city. The stars we see are like the downtown lights viewed from an airplane at night, brilliant and attention-grabbing, but representing only a tiny fraction of the metropolitan area below. The true boundary of this cosmic city extends into the darkness, invisible to our telescopes but essential to the galaxy's existence. Without its dark matter scaffolding, a galaxy like the Milky Way would be impossible. The visible matter alone lacks the gravitational strength to hold itself together against the centrifugal forces of rotation. Our solar system orbits the galactic center at nearly 500,000 miles per hour, and at that speed we should have been flung out into intergalactic space billions of years ago. We're still here only because we're embedded in a sea of dark matter whose gravity keeps us gravitationally bound to our home galaxy. Dark matter halos are not uniform spheres. They have structure, history, and personality. Computer simulations reveal them as dynamic, evolving entities constantly being fed by streams of dark matter flowing along the cosmic web. These streams merge and collide, causing the halos to grow over cosmic time through a process scientists call hierarchical assembly, smaller dark matter structures merging to form larger ones, like tributaries joining to form ever larger rivers. When 2 dark matter halos collide and merge, their galaxies eventually follow suit. This process is happening all around us. The Milky Way's dark matter halo bears the scars of ancient mergers, streams of dark matter and disrupted stars that tell the story of smaller galaxies it has consumed over billions of years. In fact, right now, our galaxy is in the process of cannibalizing the Sagittarius dwarf galaxy, slowly shredding it apart and incorporating its stars and dark matter into our own halo. But dark matter doesn't just provide the gravitational glue that holds galaxies together, it also regulates how and where new stars are born. The distribution of dark matter determines where gas can accumulate and cool, creating the dense regions necessary for star formation. It shapes the spiral arms of disk galaxies, influences the formation of central black holes, and even affects the chemical composition of stellar populations by controlling how efficiently heavy elements are mixed throughout the galaxy. Perhaps most remarkably, dark matter appears to have played a crucial role in making our universe suitable for life. If dark matter interacted more strongly with ordinary matter, galaxies would have formed too early, when the universe was still hot and dense. If it interacted too weakly, galaxies might never have formed at all. The properties of dark matter seem to be tuned to create a universe where galaxies can form and evolve over billions of years, long enough for heavy elements to be created in stellar cores and distributed throughout space, and for planets like Earth to eventually form and support the chemistry of life. Yet for all its importance, dark matter remains profoundly mysterious. We know it's there through its gravitational effects, but we don't know what it's made of. Is it composed of exotic particles left over from the Big Bang? Primordial black holes formed in the universe's infancy? Something even stranger that we haven't imagined yet? Underground laboratories around the world are searching for dark matter particles, hoping to catch one in the act of colliding with ordinary matter. Space-based telescopes are mapping the distribution of dark matter by observing how its gravity bends light from distant galaxies. Particle accelerators are attempting to create dark matter in controlled collisions. But so far these particles, if that's what they are, have remained stubbornly elusive. This elusiveness points to something profound about the nature of reality itself. We live in a universe where the majority of matter interacts with us only through gravity, the weakest of the fundamental forces. It's as if reality has two separate layers, the thin film of ordinary matter that we can see and touch, and the vast hidden substrate of dark matter that shapes the cosmic architecture while remaining forever beyond our direct perception. But dark matter is not the strangest resident of this hidden reality. That distinction belongs to dark energy, a force that may ultimately determine whether the cosmic web will continue to grow and evolve or slowly fade into cold emptiness. Dark energy is not just accelerating the expansion of the universe, it's writing the story of cosmic destiny with an invisible hand. Every moment that passes, every second you spend listening to these words, dark energy is making space larger, driving galaxies farther apart, and determining the ultimate fate of everything we know and love. To understand the profound implications of this force, imagine standing on a moving walkway at an airport. At first, you can easily walk against the direction of movement, making progress toward your gate. But gradually the walkway speeds up. Walking against it becomes more difficult than impossible. Eventually the walkway is moving so fast that even running at full speed, you're carried backward, away from your destination. This is happening to light itself in our expanding universe. Photons traveling through space are swimming against an increasingly strong current of expansion. For now, light from nearby galaxies can still reach us, just as you can still walk against a slow-moving walkway. But as dark energy continues to accelerate the expansion, even light will be unable to bridge the growing gaps between galaxies. We're already seeing this process begin. The most distant galaxies visible to our telescopes appear redder than they should because their light has been stretched to longer wavelengths during its journey through expanding space. This red shift is like the cosmic equivalent of a train whistle dropping in pitch as it speeds away from you, except instead of sound waves being stretched, it's light waves being pulled apart by the expansion of space itself. In the far future, as dark energy becomes increasingly dominant, this process will accelerate dramatically. Galaxies beyond our immediate local group will fade from view as their light becomes too red-shifted to detect. Future astronomers, billions of years from now, will look out at a universe that appears nearly empty, not because galaxies have been destroyed, but because the space between them has expanded so much that light can no longer make the journey. But dark energy's influence extends far beyond just making distant objects invisible. It's fundamentally altering the balance of forces that govern cosmic evolution. For the first several billion years after the Big Bang, matter and gravity dominated the universe's development. Dense regions became denser, pulling in surrounding material to build the first stars, galaxies, and galaxy clusters. The cosmic web grew more intricate and interconnected over time. Dark energy has reversed this process. About 6 billion years ago, roughly when our solar system was forming, dark energy became the dominant component of cosmic energy density. From that moment forward, the universe shifted from a construction phase to a dissolution phase. Instead of building larger and more complex structures, the cosmos began pulling itself apart. This transition has profound implications for the future of life and intelligence in the universe. Star formation, which depends on gravity's ability to compress gas clouds, is becoming increasingly difficult as dark energy drives matter apart. The rate at which new stars are born has already peaked and begun to decline. Eventually, as the raw materials become too dispersed, star formation will cease entirely. The cosmic web itself is being stretched and weakened. The filaments that connect galaxy clusters are becoming thinner and more tenuous. Eventually, they will snap, leaving each cluster isolated in an ocean of expanding space. Even within galaxy clusters, dark energy will gradually overcome the gravitational binding, dispersing individual galaxies into the cosmic void. If dark energy continues to behave as it does today, the universe will enter what cosmologists call the Big Rip scenario. Far in the future, trillions upon trillions of years from now, the expansion will become so violent that it will overcome all the fundamental forces. First, galaxy clusters will be torn apart, then individual galaxies, then solar systems. Eventually, even atoms themselves will be shredded as space expands faster than the speed of light. But there's another possibility. Dark energy might not remain constant forever. It could weaken, strengthen, or even reverse direction. If it weakens sufficiently, gravity might regain control, eventually halting the expansion and pulling the universe back together in a big crunch. If it strengthens beyond certain limits, the Big Rip could happen sooner than expected. The truth is, we don't know what dark energy will do because we don't understand what it is. It could be the cosmological constant that Einstein first proposed and later regretted, a fixed property of space itself. It could be a dynamic field that changes over time. It could be evidence that our understanding of gravity breaks down on cosmic scales, or it could be something completely beyond our current theoretical framework. What we do know is that dark energy has transformed our universe from a place where complexity and structure naturally increase over time into one where they are fighting a losing battle against dissolution and isolation. In doing so, it has made our current cosmic epoch, when galaxies are still forming stars, when planets can still host life, when intelligence can still contemplate the cosmos, precious beyond measure. We exist during a brief golden age of cosmic evolution, a fleeting moment when the universe is neither too young and chaotic nor too old, and dispersed to support the complexity that makes life and consciousness possible. Dark energy is the timekeeper of this golden age, and by all accounts it's counting down to an ending we're only beginning to understand. But perhaps that's what makes our existence so remarkable. In a universe shaped by invisible forces, where ordinary matter represents just 5% of reality, where dark energy is slowly erasing the cosmic architecture that makes galaxies possible, consciousness has emerged to witness and understand these profound mysteries. We are the universe becoming aware of its own hidden depths, even as those depths conspire to ensure that such awareness may be temporary. The dark architecture of the cosmos, built from dark matter, driven apart by dark energy, organized into a web of invisible filaments, is not just the stage on which the cosmic drama unfolds. It is the drama itself, a story of construction and dissolution, of structure and entropy, of a universe that builds complexity just long enough for that complexity to turn around and marvel at the darkness from which it emerged. This invisible scaffolding, this dark architecture that shapes reality itself, has been quietly building cosmic cities for nearly 14 billion years. Vast congregations of galaxies, stellar nurseries where new suns are born, and spiral highways of stars stretching across hundreds of thousands of light years. But to understand how these cosmic cities actually work, how they create the elements that make planets possible, how they forge the building blocks of life itself in the nuclear furnaces of dying stars, we need to step inside these galactic metropolises and witness the epic cycles of stellar birth and death that have been sculpting the universe since the first lights flickered on in the cosmic dark. Chapter 3: Stellar Cities and Cosmic Evolution. You're holding a penny in your hand. That copper, it was forged in the death throes of a star that exploded billions of years ago. The iron in your blood, created in the nuclear furnace of a stellar giant 50 times more massive than our sun. The calcium in your bones, the oxygen you breathe, the carbon that forms the backbone of every molecule in your body, all of it was manufactured in stellar factories scattered across the cosmos and delivered to Earth through the most spectacular fireworks show the universe has ever known. You are not just made of stardust. You are the direct descendant of cosmic catastrophes so violent and beautiful that they literally built the periodic table one element at a time across billions of years. This is the story of how the universe learned to create complexity from simplicity, life from lifelessness, and ultimately you from the ashes of ancient suns. When the universe was young, just 200 million years old, it was a very different place. Imagine a cosmos filled with nothing but the two simplest elements, hydrogen and helium. No carbon, no oxygen, no silicon or iron. Just an endless sea of the most basic building blocks, drifting in a darkness that had never known starlight. But within this seemingly barren landscape, something extraordinary was happening. Gravity, that patient architect of the cosmos, was pulling these primordial gases together into vast, invisible clouds. These weren't the gentle, gradual collapses we see in today's star-forming regions. These were monstrous accumulations of matter, growing into stellar behemoths that would dwarf our sun by factors of 50, 100, even 200 times. These first stars, astronomers call them population 3 stars, were nothing like the stars we see today. Without heavier elements to help them radiate away heat, they burned incredibly hot and incredibly bright. If you could somehow transport yourself back to witness their birth, you'd see scattered across the early universe brilliant blue-white beacons, each one blazing with the intensity of millions of modern suns. But here's the beautiful tragedy of these cosmic pioneers. Their very perfection was their doom. The more massive a star, the faster it burns through its nuclear fuel. While our sun will shine steadily for 10 billion years, these stellar giants lived fast and died spectacularly, burning out in just a few million years, a cosmic heartbeat. And when they died, They didn't fade quietly into the night. They exploded a supernova so powerful that each one briefly outshone entire galaxies. In those moments of destruction, something miraculous happened. The incredible temperatures and pressures inside these dying stars created the first heavy elements the universe had ever known. Carbon, nitrogen, oxygen, magnesium, silicon, iron. The entire periodic table was born in the nuclear furnaces of these ancient giants. But creating these elements was only half the story. The supernova explosions that ended these stellar lives scattered this precious cargo across millions of light-years of space, seeding the cosmos with the raw materials needed to build planets, atmospheres, oceans, and eventually life itself. The first generation of stars had to die so that everything else could live. But how did this stellar sacrifice actually build the cosmic cities we call galaxies? In the aftermath of those first stellar explosions, the universe was no longer the simple place it had been. Now it was enriched with heavy elements, but more importantly, it was beginning to develop structure. Remember that invisible scaffolding of dark matter we discovered in our last chapter? Now it was time for that cosmic architecture to reveal its purpose. Think of galaxy formation like the growth of a great city, but played out over billions of years and across distances that make our solar system look like a grain of sand. It starts with the dark matter, those invisible halos that act like gravitational foundations. Just as a city needs bedrock to build upon, galaxies needed these dark matter structures to provide the gravitational framework for everything else. But unlike human cities that grow outward from a center, galaxies grew from the inside out and the outside in simultaneously. Streams of gas would flow along the dark matter filaments we explored earlier, following the path of least resistance through the cosmic web. When these streams converged at the intersections of dark matter halos, they would begin to swirl and collapse, heated by their own gravitational energy until they glowed. Here's where the story becomes almost magical. As these vast rotating disks of gas began to settle into stable orbits, they would fragment into smaller clouds. Each fragment would collapse further, heating up until nuclear fusion ignited and a new star would blaze to life. Not just one star, but millions upon millions, all born from the same rotating disk of gas and dark matter. Some of these early galaxies were gentle spiral dancers like our own Milky Way, with graceful arms sweeping through space as they rotated. Others were more chaotic, elliptical giants that had formed through violent collisions and mergers, their stars scattered in seemingly random orbits around massive central bulges. And at the heart of virtually every large galaxy, something even more extraordinary was taking root. Supermassive black holes, millions or even billions of times more massive than our Sun. These weren't destroyers of galaxies, they were their engines. As matter spiraled into these cosmic drains, it would heat up and shine more brilliantly than all the stars in the galaxy combined, creating beacons so bright they could be seen across the entire observable universe. The early universe was a violent place. Galaxies didn't form in isolation. They crashed into each other, merged, tore each other apart, and reformed in an endless cosmic dance. Each collision would trigger new waves of star formation as gas clouds were compressed and heated. Some galaxies would be completely consumed by their larger neighbours. Others would emerge from these encounters transformed, their original spiral structures replaced by the more chaotic elliptical shapes. But through all this apparent chaos, a deeper order was emerging. The largest galaxies began to attract smaller ones, forming clusters held together by their combined gravitational pull. These clusters would then attract other clusters, building ever larger structures. Superclusters containing thousands of galaxies spread across hundreds of millions of light years. By the time the universe was just a few billion years old, it had transformed from a smooth, featureless expanse into a vast cosmic city filled with billions of galaxies, each containing billions of stars. But there's one particular galaxy in this vast metropolis that deserves special attention: our own cosmic home. Every night, if you can escape the glow of city lights, you can see the edge of our galaxy stretching across the dark sky like a river of faint starlight. The ancient Greeks called it Galaxius Kyklos, the Milky Circle. We know it simply as the Milky Way. But what exactly are you seeing when you look up at that band of light? You're looking at our cosmic home from the inside, edge on, like trying to map the layout of a vast city while standing in the middle of one of its neighbourhoods. Our solar system sits about 26,000 light-years from the galactic centre, roughly two-thirds of the way out from the core, in what astronomers have poetically named the Orion Arm, a minor spiral arm tucked between two major ones. If you could somehow step outside our galaxy and view it from above, you'd see something magnificent, a grand spiral with four major arms sweeping out from a bright central bulge, the whole structure rotating like a cosmic pinwheel. The entire galaxy spans 100,000 light-years from edge to edge and contains somewhere between 200 and 400 billion stars, so many that if you counted one star every second, it would take you over 10,000 years just to count them all. But the Milky Way is far from a peaceful suburban neighbourhood. At its very heart lurks a supermassive black hole called Sagittarius A star, containing the mass of 4 million suns compressed into a region smaller than our solar system. We can't see this monster directly, it's hidden behind vast clouds of interstellar dust, but we can watch stars orbiting around it at speeds of up to 5,000 miles per second, their paths bent into tight ellipses by gravitational forces beyond imagination. The remarkable thing about our location in the galaxy is just how perfect it is for the development of life. We are positioned in what astronomers call the galactic habitable zone, far enough from the chaotic centre to avoid deadly radiation and gravitational disruptions, but close enough to have access to the heavy elements created by generations of stellar death and birth. We're also located between the major spiral arms, in a relatively stable region where we're not constantly bombarded by the shock waves from massive star formation or frequent supernova explosions. But our galaxy hasn't always been the stable, majestic spiral you might imagine. It's a cannibal that has grown by consuming smaller galaxies throughout its history. The evidence is written in the stars themselves, streams of ancient stars that orbit our galaxy in the wrong direction, the remnants of smaller galaxies that were torn apart and digested by the Milky Way's gravitational appetite. Even now, our galaxy is actively feeding. The Sagittarius dwarf galaxy is being slowly shredded and consumed, its stars scattered in long streams that wrap around our galaxy like ribbons. The large and small Magellanic Clouds, those companion galaxies visible from the southern hemisphere, are slowly spiralling inward, destined to be absorbed in the distant future. And speaking of the future, our galaxy has an appointment with destiny. In about 4.5 billion years, the Milky Way will collide with our nearest large neighbour, the Andromeda Galaxy. Don't worry, the distances between stars are so vast that very few individual stars will actually collide. Instead, the two galaxies will merge in a gravitational ballet lasting billions of years, ultimately forming a single larger elliptical galaxy that astronomers have already nicknamed Milkomeda. Our galaxy is just one of hundreds of billions scattered throughout the observable universe, each one a city of stars with its own history, its own structure, its own collection of worlds. But just how many galaxies are out there, and what do they tell us about the scale of everything that exists? In 1995, astronomers pointed the Hubble Space Telescope at what appeared to be an empty patch of sky, a region so unremarkable that it seemed to contain nothing but darkness. They called it the Hubble Deep Field, and what they discovered revolutionized our understanding of the universe's true scale. In that tiny slice of sky, no bigger than a grain of sand held at arm's length, Hubble revealed over 3,000 galaxies, not stars, galaxies, each one containing billions of stars, some spiral, some elliptical, some irregular, stretching back through time to when the universe was less than 1 billion years old. If such an apparently empty region of space could contain thousands of galaxies, what did that say about the universe as a whole? The mathematics are staggering. There are approximately 2 trillion galaxies in the observable universe. That's 2 trillion separate cosmic cities, each one an island universe in its own right. To put this in perspective, there are more galaxies in the observable universe than there are grains of sand on every beach on Earth. But even these numbers don't capture the full scope of what we're seeing when we look deep into space. When astronomers observe distant galaxies, they're not just seeing across space, they're seeing across time. Light travels at a finite speed, so the farther away a galaxy is, the further back in time we're seeing it. The most distant galaxies visible to our most powerful telescopes appear as they were when the universe was less than 5% of its current age. This gives us something extraordinary, a cosmic time machine. By looking at galaxies at different distances, we can actually watch the universe evolve. We can see how galaxies looked in their youth, compare them to mature galaxies nearby, and piece together the story of cosmic evolution across 13.8 billion years. What that story reveals is a universe that has grown more complex and more beautiful over time. The earliest galaxies were smaller, more chaotic, filled with massive stars that burned bright and died young. As time passed, galaxies grew larger through mergers and accretion. They developed more structure. The graceful spiral arms we see in galaxies like our own. Star formation became more efficient and more sustainable. But perhaps most remarkably, this cosmic census reveals something profound about our place in the universe. Despite containing trillions of galaxies, each with billions of stars, many of which likely have planetary systems, the universe still appears to be mostly empty. The average distance between galaxies is about 20 times their diameter. Imagine cities where the space between buildings was 20 times wider than the buildings themselves. This vast emptiness means that for all the complexity and beauty we've discovered, most of the universe remains unexplored territory. Each galaxy is like an island universe, separated from its neighbours by oceans of nearly empty space, and yet gravity still connects them all, holding clusters together, shaping the cosmic web, writing the large-scale structure of everything that exists. We've traced the universe from its first stars to the vast galactic metropolises of today, but our journey through cosmic evolution is far from over. These stellar cities we've explored are just the visible tip of a much deeper mystery, one that will challenge everything we think we know about the nature of reality itself. From a single point smaller than an atom, the universe has grown into a vast cosmic web containing trillions of galaxies, each one a stellar city with its own history written in starlight. We've seen how the first stars had to die to create the elements of life, how gravity sculpted those elements into the majestic spirals and ellipticals that populate the cosmos today, and how our own Milky Way found its perfect place in this grand cosmic symphony. But as we stand here on Earth, looking out at this vast stellar metropolis, a profound question emerges from the data. If the observable universe alone contains more galaxies than there are grains of sand on every beach on Earth, and if each galaxy contains billions of stars, many with their own planetary systems, then just how big is everything that actually exists? The answer to that question will take us beyond everything we can see, beyond everything we can measure, and into realms where the very concepts of size and scale begin to break down. Because the universe we've been exploring, vast as it is, might be just the tiniest fraction of a reality so large that it defies not just imagination, but the very possibility of human comprehension. The cosmic cities we've discovered are magnificent, but they may be just the first neighborhoods in an infinite metropolis that stretches beyond all horizons, beyond all measurement, beyond all hope of exploration. And that's where our journey takes us next, into the scale of everything. Chapter 4. The Scale of Everything. Picture this. You're standing on a beach, holding a single grain of sand between your fingers. Now imagine that this grain represents our entire Milky Way galaxy, home to 400 billion stars, including our Sun. If that's true, then the number of galaxies in the observable universe exceeds every grain of sand on every beach in every desert on the entire planet Earth. And that staggering number? It might represent less than 1% of what actually exists. Tonight, we're going to measure the unmeasurable and attempt to grasp the ungraspable. We're going to explore the true scale of everything. How do you measure the distance to something so far away that its light has been travelling toward you for billions of years? Longer than Earth has existed? It sounds impossible. Yet astronomers do it every day, using cosmic lighthouses scattered across the universe. The story begins with a remarkable woman named Henrietta Swan Leavitt, working at Harvard Observatory in 1908. While examining photographic plates of distant stars, she noticed something extraordinary. Certain stars, called Cepheid variables, pulsed with mathematical precision. The brighter the star, the slower it pulsed. This relationship was so reliable that by timing a Cepheid's pulse, you could determine its true brightness, and if you knew how bright it really was versus how bright it appeared from Earth, you could calculate exactly how far away it was. Leavitt had discovered the universe's first standard candle. Like knowing the brightness of a streetlight lets you judge its distance in fog, Cepheids became cosmic streetlights, allowing us to measure distances across millions of light years. But Cepheids can only take us so far. For the most distant galaxies, astronomers needed something even brighter, and they found it in stellar catastrophes. When certain white dwarf stars reach a critical mass, they explode as type-wire supernovae, each one releasing roughly the same amount of energy. These cosmic explosions are so brilliant, they can be seen from billions of light-years away, serving as standard candles for the deepest reaches of space. Using these stellar beacons, astronomers constructed a cosmic distance ladder, each rung extending our reach further into the universe. From parallax measurements of nearby stars to Cepheids in neighboring galaxies, to supernovae in the most distant reaches of space, each method calibrated against the next, creating a chain of measurements stretching across the cosmos. Yet even with these tools, what they discovered challenged everything they thought they knew about the size of reality itself. Here's a puzzle that stumped even Einstein. If the universe is 13.8 billion years old, Why can we see objects that are 46.5 billion light-years away? Shouldn't the most distant things we can observe be only 13.8 billion light-years away? The distance light could have travelled since the beginning of time. The answer reveals something profound about the nature of space itself. Imagine you're standing on a moving walkway at an airport throwing a ball to a friend who's also on the walkway but moving in the opposite direction. The ball's speed relative to the ground isn't just how fast you threw it, it's that speed plus the speed of the walkway. Now imagine the walkway itself is accelerating, stretching as your ball travels through the air. This is what happens to light travelling through expanding space. As photons journey from distant galaxies toward us, the space they're travelling through is stretching, carrying those galaxies further away even as their light approaches us. A galaxy that emitted light 13 billion years ago, when it was much closer to us, is now 46 billion light-years away because space itself has been expanding during the entire journey of that light. This creates our cosmic horizon, a sphere 46.5 billion light-years in radius, centered on Earth. Everything within this sphere represents the observable universe, the entirety of space and time from which light has had enough time to reach us since the Big Bang. But here's what keeps astronomers awake at night. This observable sphere isn't fixed. Every second as time passes, our cosmic horizon grows by 300,000 kilometers. The distance light travels in 1 second. We're constantly seeing new regions of space for the first time, as light that has been travelling for nearly 14 billion years finally reaches our telescopes. Yet for all its mind-bending size, the observable universe might be just a tiny fragment of what actually exists. Standing at the edge of our cosmic horizon is like standing at the shore of an ocean, knowing that vast continents lie beyond your sight, but having no way to see them. Which raises the question, what lies beyond the edge of everything we can ever hope to observe? Imagine Earth as a marble floating in the middle of the Pacific Ocean. Everything you can see to the horizon represents the observable universe. Now imagine that the Pacific Ocean is just one small bay and a coastline that stretches around an entire planet. That planet orbits a star, which orbits within a galaxy, which is part of a local group which belongs to a supercluster. And even all of that might be negligible compared to what lies beyond our cosmic horizon. The latest computer simulations suggest something extraordinary. If we could somehow step outside our observable bubble and look around, we might see a universe that extends for trillions upon trillions of light-years in every direction. The entire observable universe, every galaxy, every star, every planet we've ever detected, would appear as a microscopic speck in an ocean of space so vast it defies comprehension. Consider this. If the observable universe were shrunk down to the size of a grain of sand, the actual universe might be larger than Earth. And Earth, in this analogy, might itself be a grain of sand compared to the true scope of reality. What fills this unimaginably vast space? More of the same, galaxies upon galaxies organized into the same cosmic web structure we see in our local region. Somewhere out there, separated by distances we cannot fathom, there might be regions of space that look exactly like our local group of galaxies. In fact, in a universe this large, there might be countless regions that are identical to ours in every detail, including planets exactly like Earth, with people exactly like you, reading these exact words. This isn't science fiction. It's a mathematical consequence of infinity. In an infinite universe with finite building blocks, atoms arranged in planets, stars and galaxies, every possible combination must occur, and must occur infinitely often. There might be another version of you just a few trillion light-years away, living a life identical to yours except for one small detail. and another version where every detail is different. But even this mind-bending possibility pales beside an even more fundamental question. What is the actual shape of the space we inhabit? Take a sheet of paper and draw two parallel lines. Now ask yourself, will these lines ever meet? Your immediate answer is probably no. That's what parallel means. But what if that sheet of paper is actually wrapped around a sphere? Suddenly those parallel lines converge at the poles. The same question applies to the universe itself. What is the geometry of space? And the answer determines whether reality is finite or truly infinite. Einstein's general relativity revealed that space isn't just an empty stage where cosmic drama unfolds. Space itself can be curved by the matter and energy it contains. Picture a stretched rubber sheet with bowling balls placed on it. The balls create depressions, and marbles rolled nearby will curve around these depressions. This is how mass curves space-time, creating what we experience as gravity. But what about the overall curvature of space itself? There are three possibilities, each with profound implications for the nature of reality. If space has positive curvature, like the surface of a sphere, then parallel lines eventually converge, and the universe is finite. Travel far enough in any direction, and you'd eventually return to your starting point like Magellan circumnavigating the Earth. In such a universe, there would be a finite number of atoms, a finite number of possible arrangements, and therefore a finite, though unimaginably large, amount of stuff. If space has negative curvature, like a saddle shape, then parallel lines diverge and space stretches infinitely in all directions. In this hyperbolic universe, there would be infinite space, infinite matter, and infinite possibilities. The third option is flat space, the geometry we learned in school, where parallel lines never meet and space extends infinitely in all directions like an endless sheet of paper. In a flat universe, infinite space contains infinite galaxies arranged in infinite variations. So which is it? This is where precision measurements become crucial. Scientists have measured the cosmic microwave background radiation, the afterglow of the Big Bang, with exquisite precision, looking for tiny variations that would reveal space's curvature. The answer they found is remarkable. Space appears to be flat, or so close to flat that we cannot detect any curvature. This means our universe is most likely infinite, not just really, really big, but truly infinite. Every possible arrangement of matter exists somewhere. Every possible version of history plays out in some distant region of space. Every story that could be told is being lived by someone somewhere in the boundless expanse of reality. But even this mind-shattering possibility might be just the beginning of something far stranger. Standing here on Earth, looking up at the night sky, we can see perhaps 3,000 stars with the naked eye. With our most powerful telescopes, we can observe hundreds of billions of galaxies, each containing hundreds of billions of stars. And if our measurements are correct, all of this, every photon of light we've ever collected, every galaxy we've ever catalogued, every discovery we've ever made, represents an infinitesimally small fraction of an infinite universe. But what if even infinity isn't enough? What if our infinite universe is just one bubble in an endless foam of realities, each with different laws of physics, different constants of nature, different possibilities for matter and life? What if the very concepts of space and time that seem so fundamental to our existence are just local features of our particular cosmic neighborhood? Recent discoveries in quantum mechanics and cosmology suggest that reality might be far stranger than even an infinite universe can accommodate. They point toward a multiverse, not just multiple galaxies, but multiple universes, each as complete and real as our own. The question is no longer just, how big is everything? The question has become, how many everythings are there? Chapter 5. Beyond the Single Universe. What if I told you that right now, as you listen to these words, there might be another version of you in another universe who chose not to listen? In fact, there might be infinite versions of you. One who became a professional musician, one who never learned to read, one where you were never born at all because your parents never met. Sound like science fiction? Welcome to the cutting edge of modern physics, where the impossible has become not just possible but probable. For most of human history, we've assumed we live in the universe, singular, unique, all there is. But recent discoveries in quantum mechanics and cosmology suggest something far more extraordinary. Our universe might be just one bubble in an infinite cosmic foam, one branch on an endlessly growing tree of reality. The implications are staggering, beautiful, and deeply unsettling. Let's start with something simple, a coin flip. Heads or tails, 50-50 odds, one outcome. Or so we thought. In 1957, a young physicist named Hugh Everett III proposed something radical. What if both outcomes actually happen? What if, at the moment of the flip, reality itself splits into two parallel branches? One where the coin shows heads, another where it shows tails. This isn't philosophical speculation, it's the many worlds interpretation of quantum mechanics, and it emerges from one of the most successful theories in all of science. Here's the thing about the quantum world. Particles don't behave like the objects we know. An electron doesn't orbit an atom like a planet orbits the sun. Instead, it exists in what physicists call a superposition. It's simultaneously in multiple places at once, like a ghost that haunts every possible location around the nucleus. But here's where it gets strange. The moment we try to observe that electron, to pin down exactly where it is, the ghostly superposition collapses into a single, definite location. The standard interpretation says the other possibilities simply disappear, vanishing into mathematical nothingness. But Everett asked a profound question. What if they don't disappear? What if every possibility becomes real in its own separate universe? Picture this. Every time a quantum event occurs, and they're happening trillions of times per second in every atom of your body, reality branches. One branch for each possible outcome. It's like a cosmic tree that never stops growing, sprouting new branches with every quantum decision. In one branch, that electron appears on the left side of the atom. In another, it appears on the right. Both are equally real, equally valid universes. The mathematics are elegant, even beautiful. There's no need for the mysterious collapse that has puzzled physicists for decades. Every possibility predicted by quantum mechanics simply plays out in its own universe. The reason we see only one outcome isn't because the others don't happen, it's because we can only experience one branch of reality at a time. Think about the implications. Every decision you've ever made, every random event that shaped your life, has spawned countless parallel worlds. There's a universe where you said yes instead of no to that job offer, where you took a different route to work and avoided that accident, where you never met the person who became your best friend. These aren't fantasies. In the many worlds framework, they're as real as the world you're experiencing right now. But if infinite universes are being created every moment, how do we make sense of probability? If everything happens, why do some outcomes seem more likely than others? The answer lies in the quantum amplitude, a measure of how thick each branch of reality is. Highly probable outcomes correspond to thick branches containing many copies of you, while unlikely outcomes create thin branches with fewer copies. you're most likely to find yourself in a thick branch, which is why quantum mechanics seems to follow probability rules, even though everything actually happens. This raises an unsettling question. If there are infinite versions of you across infinite universes, which one is the real you? The disturbing answer might be that they all are. Every possible version of your life is playing out somewhere in the vast tree of parallel realities. But the quantum multiverse is just the beginning. If our understanding of the early universe is correct, there might be an even more mind-bending form of parallel reality, one where entire universes bubble into existence like foam on an infinite cosmic sea. Imagine blowing soap bubbles in your backyard. Each bubble forms, expands, and eventually pops. Now imagine that process never stops. An eternal bubble machine creating an endless stream of bubbles, each one a complete universe with its own space, time, and physical laws. This isn't a metaphor. According to our best theories of cosmic inflation, this might literally be how reality works. To understand eternal inflation, we need to go back to the very beginning, not just of our universe, but of the process that created it. In those first incomprehensibly brief moments after the Big Bang, space itself underwent a period of exponential expansion called cosmic inflation. In less than a trillionth of a trillionth of a trillionth of a second, a region smaller than a proton expanded to the size of a basketball. It's the most violent, rapid transformation in the history of physics. But here's the crucial insight. Inflation might not have stopped everywhere at once. Picture a bubbling pot of water. Most of the water is boiling vigorously, with bubbles forming and rising to the surface. But some bubbles form, rise partway, then stop, creating pockets of calm water within the churning chaos. In cosmic inflation, our universe might be like one of those calm pockets, a region where inflation stopped and normal space-time began, surrounded by an ocean of space that's still inflating exponentially. The physicist Alan Guth, who first proposed cosmic inflation, realized that once this process begins, it becomes eternal. The inflating regions grow so fast that even though some pockets stop inflating and become universes like ours, the total volume of inflating space actually increases. It's like trying to deflate a balloon by poking holes in it, but the balloon is expanding faster than you can poke. The holes become individual universes, but the balloon itself keeps growing forever. What does this mean? It means our Big Bang wasn't the beginning of everything. It was just the moment when our local pocket of space-time stopped inflating and began the more sedate expansion we observe today. Meanwhile, all around us, separated by unimaginable distances of still inflating space, other universes are popping into existence like bubbles in champagne. Each bubble universe is causally disconnected from all the others. No light, no matter, no information can travel between them, because the inflating space between them expands faster than anything can cross it. They're not just far away, they're unreachable by the very structure of space-time itself. But here's where it gets even stranger. The quantum fluctuations that drive inflation are random, which means each bubble universe might have different physical properties. The strength of gravity, the mass of the electron, the number of spatial dimensions, all the constants and laws we consider fundamental might be different in other bubble universes. Some might have physics so alien that stars never form. Others might be filled with types of matter we can't even imagine. The numbers are staggering. If eternal inflation is correct, then the total number of universes is not just large, it's infinite. And in an infinite multiverse, every possible variation occurs not just once, but infinitely many times. There are infinite universes exactly like ours, infinite universes where Earth never formed, infinite universes where the laws of physics are so different that consciousness could never emerge. This leads to a profound realization. We might live in what cosmologists call a pocket universe, a small, finite region of space-time embedded in an infinite, ever-growing multiverse. Our observable universe, vast as it seems to us, would be like a single grain of sand on an infinite beach. The beauty of eternal inflation is that it's testable, at least in principle. The boundaries between different inflating regions might leave subtle signatures in the cosmic microwave background radiation, the afterglow of our own Big Bang. Some cosmologists claim to have found hints of these signatures, though the evidence remains controversial. But eternal inflation raises as many questions as it answers. If every possible universe exists, how do we explain why we find ourselves in one that seems so finely tuned for the existence of stars, planets, and life? The answer might lie in a principle so controversial it makes physicists uncomfortable: the anthropic principle. Here's a puzzle that has kept physicists awake at night for decades. Our universe appears to be exquisitely fine-tuned for the existence of life. Change the strength of gravity by just 1 part in 10 circumflex 40, and stars would either burn out too quickly or never ignite at all. Adjust the strong nuclear force by a few percent, and atomic nuclei would fly apart, making chemistry impossible. Tweak the cosmological constant, the energy of empty space itself, by an infinitesimally small amount, and the universe would either collapse immediately or expand so fast that galaxies could never form. The numbers are so precise, the balance so delicate, that it seems almost impossible that such a universe could exist by chance. It's like walking into a casino and winning the lottery, then the slot machines, then every hand of poker, then having the roulette ball land on your number 100 times in a row. The odds are so astronomical that you'd be justified in suspecting the game was rigged. But rigged by whom? For much of the 20th century, this fine-tuning problem led some scientists toward uncomfortable territory. The suggestion that the universe was designed, that some intelligence deliberately set the cosmic dials to values that would allow stars, planets, and eventually life to emerge. It was a conclusion that made many physicists deeply uneasy, not because they had anything against the possibility of design, but because it seemed to take the question outside the realm of science altogether. Enter the anthropic principle, first articulated by theoretical physicist Brandon Carter in 1973. The idea is elegantly simple and deeply unsettling. We observe a universe that appears fine-tuned for life, not because it was designed that way, but because we couldn't observe it any other way. In a universe where stars never formed or chemistry was impossible, there would be no galaxies, no planets, no evolution, no consciousness, and therefore no observers to notice that the universe was hostile to life. Think of it this way. Imagine a vast field scattered with thousands of mousetraps, only a few of which are baited with cheese. A mouse wandering through this field will obviously end up at one of the baited traps, not because the field was designed for mice, but because those are the only traps where a mouse would survive long enough to notice its surroundings. Similarly, we find ourselves in a life-friendly universe, not because most universes are life-friendly, but because we could only evolve in one of the rare universes where the conditions are just right. This reasoning becomes compelling when combined with the multiverse theories we've been exploring. If eternal inflation creates infinite bubble universes with different physical constants, then somewhere in that vast multiverse There must be universes with every possible combination of physical laws. Most would be sterile, either collapsing immediately, expanding too rapidly for structure to form, or lacking the right conditions for complex chemistry. But a tiny fraction would have the delicate balance necessary for stars, planets, and life. The anthropic principle doesn't predict what values the physical constants should have. It simply explains why we observe values that seem improbably life-friendly. We're like lottery winners marveling at our incredible luck, not realizing that millions of other tickets were sold, but only the winners are around to be surprised by their good fortune. But the anthropic principle comes in two flavors, and the distinction is crucial. The weak anthropic principle simply states that we observe physical constants compatible with life because we exist to observe them. This is almost a tautology, a statement so obviously true that it borders on meaningless. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop within it at some point in its history. The strong version makes physicists nervous because it seems to imply purpose or design, that the universe somehow knows it needs to create observers. But when combined with multiverse theory, even the strong anthropic principle becomes naturalistic. If there are infinite universes with all possible physical constants, then by pure statistical necessity, some fraction must be compatible with the emergence of consciousness. This leads to testable predictions. If the anthropic principle is correct, we should find ourselves in a universe that's not perfectly optimized for life, but rather one that's good enough, fine-tuned within the margins necessary for complexity to emerge, but not beyond. And indeed, when we look closely at our cosmic environment, we find a universe that seems to thread the needle between the extremes that would make life impossible. Yet, the anthropic principle raises deeply unsettling questions about the nature of scientific explanation. Are we abandoning the search for deeper physical principles in favor of cosmic coincidence? Or are we finally grappling with the true nature of reality? That consciousness might be a fundamental feature of the multiverse, not an accidental byproduct? The debate rages on in cosmology conferences and physics journals, but one thing is becoming clear: our universe's apparent fine-tuning might not be evidence of design, but rather evidence that we live in a much stranger and more vast reality than we ever imagined. A reality where every possible universe exists, and conscious observers inevitably find themselves in the tiny fraction capable of creating conscious observers. But this raises an even more mind-bending possibility. If every possible universe exists in the multiverse, then the distinction between possible and actual might be meaningless. Perhaps everything that can exist does exist. Not just other universes, but other versions of physical law, other forms of mathematics, other types of logic itself. What if I told you that right now you exist not just in this universe, but in every universe that could possibly contain a being exactly like you? What if every mathematical structure that could describe a reality actually is a reality? Welcome to the most radical multiverse theory of all, the mathematical universe hypothesis, proposed by cosmologist Max Tegmark. To understand this mind-bending idea, we need to think about the relationship between mathematics and physical reality. For centuries, scientists have marveled at what physicist Eugene Wigner called the unreasonable effectiveness of mathematics in the natural sciences. Why should abstract mathematical equations describe the behavior of real particles, forces, and fields with such uncanny precision? Why does the universe seem to run on mathematical principles? Most physicists assume that mathematics is a language we use to describe reality, a powerful tool for understanding the world, but not the world itself. But Tegmark asks a provocative question. What if we have it backwards? What if physical reality isn't described by mathematics? What if it is mathematics? The idea builds on a principle that philosophers call the unreasonable effectiveness of mathematics. Every successful physical theory, from Newton's laws to Einstein's relativity to quantum mechanics, is ultimately a mathematical structure. Remove all the human language, all the physical intuition, all the mental pictures, and what remains is pure mathematics, equations, symmetries, and abstract relationships. But here's Tegmark's radical insight. If our physical reality corresponds to a mathematical structure, and if mathematical structures exist independently of physical reality, then other mathematical structures should correspond to other physical realities. Every consistent mathematical framework, every possible set of equations that doesn't lead to logical contradictions, should describe an actual universe. This isn't just speculation. Consider the different types of multiverse we've already discussed. The quantum multiverse corresponds to the mathematical structure of quantum mechanics, where every possible measurement outcome occurs in some branch of reality. The inflationary multiverse corresponds to the mathematical structure of general relativity and quantum field theory, where different regions of space-time can have different physical parameters. But the mathematical universe hypothesis goes much further. It suggests that every possible mathematical structure exists as a physical reality. Universes with different numbers of spatial dimensions, universes where time flows backwards, universes with completely different types of particles and forces, universes with mathematical laws so alien that we can't even imagine what they would be like. The implications are staggering. In this ultimate multiverse, there would be universes governed by the mathematics of cellular automata, digital realities where space and time are discrete, like pixels on a cosmic computer screen. There would be universes based on non-Euclidean geometries, where parallel lines meet and the angles of triangles don't add up to 180 degrees. There would be universes where the very concept of causation works differently, where effects can precede their causes. And somewhere in this infinite mathematical multiverse, there would be countless universes exactly like ours, governed by the same equations, with the same physical constants, even with identical copies of you reading these same words at this same moment. The only difference would be that they correspond to different mathematical structures that happen to have identical properties. This raises profound questions about the nature of existence itself. If every mathematical structure exists as a physical reality, then what makes our universe special? The answer might be nothing at all. We experience this particular mathematical structure not because it's uniquely real, but because we are part of it. Our consciousness, our memories, our entire sense of identity would be features of this specific mathematical pattern. But the mathematical universe hypothesis faces serious challenges. If every possible mathematical structure exists, then most universes would be completely chaotic. Random arrangements of particles and fields with no structure, no pattern, no possibility for complexity to emerge. These typical universes would vastly outnumber the rare orderly ones like ours, where stars and planets and life can form. This leads to what cosmologists call the measure problem. How do we calculate probabilities in an infinite multiverse? If there are infinitely many universes like ours and infinitely many chaotic universes, what does it mean to say that most universes are chaotic? Infinity minus infinity doesn't have a well-defined answer. Some physicists propose solutions involving what they call algorithmic information theory. the idea that simpler mathematical structures should be more common than complex ones. In this view, we're more likely to find ourselves in a universe corresponding to an elegant mathematical structure than in one requiring enormous amounts of information to specify. Others suggest that consciousness itself might be the key. Perhaps only mathematical structures complex enough to support observers can be considered real in any meaningful sense. This would dramatically reduce the size of the multiverse, limiting it to the subset of mathematical structures capable of generating conscious experience. The mathematical universe hypothesis remains highly speculative, pushing the boundaries of what can even be considered science, but it represents the logical endpoint of our journey through multiverse theories, the ultimate expansion of reality to include not just other universes, but every possible universe that could ever exist. Whether or not the mathematical universe hypothesis is correct, it forces us to confront fundamental questions about the nature of existence, consciousness, and reality itself. If everything that can exist does exist, then what makes our experience special? What gives meaning to our choices if every possible choice is made by some version of ourselves in some universe? These questions bring us back to an ancient philosophical puzzle that has gained new urgency in the age of multiverse cosmology. What does it mean to exist, and how do we find meaning in a reality that might be infinitely larger and stranger than we ever imagined? We began this journey asking what lies beyond our single universe, and we've discovered that the answer might be everything. Every possibility, every potential reality, every conceivable form of existence. From the branching worlds of quantum mechanics to the bubble universes of eternal inflation, from the fine-tuned realities of the anthropic landscape to the infinite mathematical structures of Tegmark's ultimate multiverse, we've seen that our cosmos might be far stranger and more vast than our ancestors ever dreamed. But these aren't just abstract theories. They emerge from our most successful descriptions of physical reality: quantum mechanics, general relativity, and the standard model of particle physics. The multiverse isn't science fiction. It's the logical consequence of taking our best scientific theories seriously. Yet, this expansion of reality raises profound questions about meaning, purpose, and our place in the cosmic order. If every possibility is realized somewhere in the multiverse, do our choices matter? If there are infinite versions of ourselves living out every conceivable variation of our lives, what makes this version special? Perhaps the answer lies not in the vastness of the multiverse, but in the simple fact that we're here to contemplate it. Consciousness, the ability to observe, to question, to wonder, might be the rarest and most precious phenomenon in all of reality. Whether we're alone in our universe or one of countless observers scattered across infinite realities, the fact that matter has organized itself into patterns capable of understanding the cosmos remains miraculous. The multiverse theories we've explored represent humanity's boldest attempt to comprehend the true scope of existence. But they also remind us that science is a never-ending journey. Each answer we discover reveals new questions. Each theory we develop opens new mysteries. The multiverse isn't the end of our cosmic story. It's just the beginning of an even grander adventure. But before we had equations and experiments to guide us toward these mind-bending possibilities, humans looked up at the same stars and asked the same fundamental questions about existence and meaning. The stories they told, myths, legends, and philosophical systems still echo in how we think about reality today, and those ancient voices might have insights that even our most advanced theories haven't fully grasped. Chapter 6. Ancient Visions and Eternal Questions. It's 25,000 years ago. A Cro-Magnon artist crouches in a cave in what will someday be called France, mixing charcoal with animal fat by flickering firelight. Above them, painted on the stone ceiling, are dots and lines, not random marks, but careful observations of the Pleiades star cluster, the phases of the moon, the journey of Venus across the night sky. This unnamed human with no telescope, no mathematics, no written language is doing something revolutionary. They're trying to make sense of the cosmos. Long before Einstein dreamed of relativity, before Hubble discovered the expanding universe, before we had any notion of dark matter or quantum mechanics, our ancestors looked up at the same stars we see today and asked the same profound questions that drive science now. Where did all this come from? What is our place in the vast dance of celestial bodies? Are we alone? These weren't just idle wonderings. They were humanity's first attempts at cosmology, and they were surprisingly sophisticated. Today we think of science and mythology as opposites, but they spring from the same well of human curiosity. Both seek to answer the ultimate questions about existence, origin and meaning. The difference isn't in the questions, it's in the methods we use to find answers. What's remarkable isn't that every human culture has a creation story. It's how similar these stories are, despite arising independently across vast distances and centuries. From the fjords of Scandinavia to the deserts of Australia, from the mountains of Tibet to the rainforests of the Amazon, humans have consistently imagined creation as emerging from darkness, chaos, or void through the action of consciousness, breath, or word. The ancient Egyptians envisioned Atum, the first god, emerging from the primordial waters of Nun and speaking the world into existence through divine utterance. Thousands of miles away, the Hebrew creation story begins with God's breath moving over the face of the deep, followed by the famous words, "Let there be light." In Hindu cosmology, the universe begins when Brahma awakens from cosmic sleep and exhales reality into being. The Big Bang Theory, with its description of everything emerging from a singular point through the fundamental forces of nature, isn't entirely different. It's the same human intuition, refined through centuries of observation and mathematics. But perhaps the most startling parallels appear when we examine concepts of cosmic time. The Norse spoke of Ragnarok, not just an ending, but a cosmic cycle where the universe dies and is reborn in endless repetition. Hindu cosmology describes kalpas, vast cycles of creation and destruction spanning billions of years, with the universe breathing in and out like a sleeping god. These aren't primitive fantasies, they're sophisticated attempts to grapple with infinity, with cycles that dwarf human comprehension. The Aboriginal Australians developed perhaps the most complex understanding of all, the dream time, where past, present and future exist simultaneously, where the landscape itself holds memory, and where creation isn't a distant event but an ongoing process. When quantum physicists tell us that time isn't linear, that the past and future might exist simultaneously in the quantum realm, they're not so far from what Aboriginal elders have taught for 50,000 years. What these stories share is a recognition that existence itself is extraordinary, that the mere fact that anything exists at all demands explanation. They understood, as we do now, that the universe didn't have to be. The fact that it is represents the deepest mystery of all. But creation stories were just the beginning. Ancient minds didn't stop at origins. They wanted to understand the architecture of reality itself. And that's where things get really interesting. In the 6th century BCE, in the Greek city of Miletos, a merchant named Thales made an observation that would change everything. Looking at fossils of sea creatures found far inland, he concluded that water was the fundamental substance from which all things emerged. Thales was wrong about water being the prime element, but he was revolutionary in his approach. He sought natural explanations for natural phenomena, no gods, no magic, just reasoned observation of the world. His student Anaximander went further. He proposed that the Earth was a cylinder floating freely in space, held in place not by Atlas or a giant turtle, but by being equidistant from all other celestial bodies. Without any modern instruments, purely through thought, he intuited one of the most difficult concepts in physics, that objects in space don't need something to rest on, they can exist in dynamic equilibrium. Anaximander also suggested that the universe was far larger than anyone imagined, filled with countless worlds like our own. 2,500 years before we discovered exoplanets, he was already envisioning them. But the real revolutionary was Democritus. Around 400 BCE, he proposed something so radical it wouldn't be accepted until the 20th century, that everything we see is made of invisible, indivisible particles moving through mostly empty space. He called them atoms, literally uncuttables, and suggested that the complexity and beauty of the world emerged from simple particles combining in countless patterns. When you bite into an apple, Democritus said, you're not experiencing the apple itself, but atoms from the apple striking atoms in your tongue and nose. Reality, he proposed, was far stranger and more subtle than our senses could directly perceive. These weren't just lucky guesses. These philosophers developed systematic ways of thinking about the cosmos that mirror modern scientific method. Start with careful observation, propose natural explanations, test ideas through logic and further observation, be willing to reject cherished beliefs when evidence demands it. Aristotle, despite being wrong about many specifics, gave us the framework for empirical investigation that still guides science today. The Greeks also gave us something else crucial: the recognition that mathematics might be the language of the cosmos. Pythagoras discovered that musical harmony could be expressed in numerical ratios, that beauty itself might have mathematical structure. Plato suggested that physical reality was just a shadow of perfect mathematical forms. When Einstein said, "God does not play dice with the universe," he was echoing Plato's conviction that beneath the apparent chaos of the physical world lies elegant mathematical order. These philosophical insights spread and evolved as they encountered other traditions, creating synthesis that would reshape human understanding of cosmic order. For over 1,000 years, human beings lived in a universe that made perfect sense. Earth sat motionless at the center of creation, with the sun, moon, planets and stars revolving around us in crystalline spheres that sang as they turned. It was beautiful, it was orderly, and it placed humanity exactly where we felt we belonged, at the center of everything. Then, in 1543, a Polish canon named Nicholas Copernicus published a book that would shatter this comfortable worldview forever. De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres, proposed something that seemed not just wrong but absurd, that the Earth moved. Copernicus wasn't the first to suggest this. Aristarchus of Samos had proposed a heliocentric model 1,800 years earlier, but the idea was so counterintuitive that even the sophisticated Greeks rejected it. After all, if the Earth was spinning, why didn't we feel it? If we were racing around the sun at tremendous speed, why didn't we fly off into space? Why didn't a dropped stone fall behind us as the Earth rotated beneath it? But Copernicus had better mathematics than his ancient predecessor, and he had something else. The courage to follow logic wherever it led, even if it challenged everything humans believed about their place in creation. His model wasn't just more elegant than the Earth-centered system, it was demonstrably more accurate at predicting planetary positions. The resistance to Copernican theory wasn't just religious, it was existential. If Earth wasn't the centre of the universe, what were we? Just another planet circling an ordinary star? The psychological impact was devastating. As John Donne wrote in 1611, "The new philosophy calls all in doubt, 'tis all in pieces, all coherence gone." But something remarkable happened as humans adjusted to this new cosmic perspective. Instead of diminishing us, it expanded our sense of wonder. Galileo, peering through his telescope, discovered that the Milky Way was composed of countless individual stars. The universe wasn't smaller without us at the centre. It was unimaginably larger. We weren't lesser for living on a planet among many. We were part of something far grander than we'd ever imagined. The Copernican revolution taught us that reality doesn't conform to our intuitions or desires. The universe doesn't care what we want to believe about our cosmic importance. But it also taught us that we're capable of transcending our limitations through reason and observation, of discovering truths that are far more wonderful than the comfortable illusions we started with. This lesson, that reality is both stranger and grander than our initial assumptions, would prove essential as humanity encountered even more mind-bending truths about space-time and our place in the cosmic order. And some of the most profound insights would come from traditions that had been contemplating infinity long before Western science was born. While Western philosophy was still grappling with the basics of natural explanation, Eastern traditions had already plunged into the deepest waters of cosmological speculation. In ancient India, around the time Greek philosophers were debating whether earth or fire was the fundamental element, Buddhist and Hindu thinkers were contemplating concepts that wouldn't appear in Western science until the 20th century: infinite time, infinite space, multiple universes, and the fundamental interconnectedness of all existence. Consider this passage from the Lotus Sutra, written over 2,000 years ago. In each atom exist 10 billion worlds. In each world exist 10 billion atoms. When modern cosmologists describe the quantum foam, the idea that at the smallest scales space and time themselves become granular and probabilistic, with virtual particles popping in and out of existence, they're describing something that Buddhist philosophers had already mapped in the realm of thought. Hindu cosmology presented timescales that boggled even sophisticated minds. A single day of Brahma, one kalpa, lasts 4.32 billion years. Brahma's entire lifespan encompasses 311 trillion 40 billion years, and this represents just one cosmic cycle among endless repetitions. When these numbers were first translated into European languages in the 18th century, they seemed like fantasy. Today, we know that the universe is about 13.8 billion years old, impressively close to the Hindu calculation for the current cosmic cycle. But the Eastern traditions went beyond mere numbers. They grappled with paradoxes that quantum physics has made central to modern cosmology. The Buddhist concept of sunyata, often translated as emptiness, doesn't mean that nothing exists, but rather that nothing exists independently. Everything arises in dependence upon everything else, in an interconnected web of cause and effect that extends across space and time. When physicists tell us that quantum entanglement links particles across vast distances instantaneously, or that the observer effect means consciousness plays a role in determining physical reality, They're describing aspects of interdependence that Buddhist philosophers have explored for millennia. The Jain tradition, even more remarkably, developed sophisticated ideas about the geometry of space and time. Jain cosmology describes the universe as having a specific shape, neither infinite nor finite, but unbounded, like the surface of a sphere. Time, they suggested, moves in cycles, but these cycles exist within larger cycles, creating complex geometries of temporal repetition. When Einstein showed that space-time itself could be curved, when cosmologists began discussing closed universe models and cyclic cosmologies, they were rediscovering territory that Jain philosophers had mapped centuries earlier. Perhaps most remarkably, these traditions understood that the ultimate questions about existence couldn't be answered through analysis alone. The Zen tradition speaks of mind only, the recognition that our concepts about the universe, however sophisticated, are still mental constructs. They point to something beyond both existence and non-existence, beyond the categories that even advanced physics uses to describe reality. This wasn't anti-scientific thinking, it was meta-scientific, recognizing that even our most sophisticated theories are still human constructs, attempting to describe something that ultimately transcends human categories. When Werner Heisenberg said, "What we observe is not nature itself, but nature exposed to our method of questioning," he was echoing insights that Eastern philosophers had reached through centuries of contemplation. These Eastern perspectives prepared the human mind for the conceptual revolutions that were coming. They showed that infinity wasn't just a mathematical abstraction, that interconnectedness wasn't just poetic metaphor, that consciousness and cosmos might be more intimately related than Western thought had ever imagined. But all of these philosophical and spiritual insights were about to be tested against the most rigorous method humans had ever developed for understanding the natural world, the systematic observation and mathematical analysis we call modern science. On the night of November 11, 1572, a young Danish nobleman named Tycho Brahe looked up at the constellation Cassiopeia and saw something impossible, a new star blazing brighter than Venus, visible even in daylight. For nearly 2 years, this supernova burned in the sky, challenging everything Europeans believed about the unchanging perfection of the heavens. But Tycho didn't just wonder, he measured. Night after night, using instruments of unprecedented precision, he recorded the star's position, brightness and colour. He was doing something revolutionary, treating the heavens not as objects of philosophical speculation, but as phenomena that could be studied with the same systematic attention given to earthly mechanics. This represented a fundamental shift in human relationship with the cosmos. For millennia, astronomy had been primarily about predicting eclipses, casting horoscopes, and creating calendars. Tycho transformed it into something new, a quantitative science aimed at discovering the actual structure and behavior of celestial objects. His protégé, Johannes Kepler, carried this revolution even further. Inheriting Tycho's meticulous observations of Mars, Kepler spent 8 years trying to fit the planet's motion into circular orbits, because circles were perfect, and surely God would use perfect shapes in constructing the heavens. But Mars refused to cooperate. Finally, in a moment of desperate inspiration, Kepler tried ellipses. The data fit perfectly. "I have stolen the golden vessels of the Egyptians to build a temple to my God," Kepler wrote, recognizing that he had discovered something profound. The universe operated according to mathematical laws that could be discovered through careful observation and analysis. regardless of what those laws did to human preconceptions about cosmic perfection. Galileo added the crucial missing piece, the telescope. Suddenly the moon revealed mountains and craters, proving it was a world like Earth, rather than a perfect celestial sphere. Jupiter showed 4 moons orbiting around it, proving that not everything in the heavens revolved around Earth. The Milky Way resolved into countless individual stars, suggesting that the universe was far larger and more populated than anyone had imagined. But the real breakthrough came when Isaac Newton connected terrestrial and celestial mechanics through his law of universal gravitation. The same force that made apples fall from trees kept planets in their orbits. The universe wasn't divided between a perfect celestial realm and an imperfect earthly one. It was all one system, operating according to discoverable mathematical principles. This was more than just scientific progress, it was a new way of being human in the cosmos. Instead of seeing ourselves as passive recipients of cosmic influence, subject to the whims of celestial gods or the predetermined fate written in the stars, we discovered that we could understand the universe through reason and observation. We weren't just in the cosmos, we could comprehend it. The implications were staggering, and would only become more so as our instruments grew more powerful and our mathematics more sophisticated. We were on the verge of discoveries that would make the Copernican revolution look modest by comparison. By the early 20th century, astronomers thought they had the universe pretty well figured out. It consisted of our Milky Way galaxy, containing perhaps 100 billion stars, floating in an infinite, static, eternal space. This seemed vast enough to satisfy any cosmic imagination. Then, in 1925, Edwin Hubble pointed the newly completed 100-inch telescope at Mount Wilson toward a fuzzy patch of light called the Andromeda Nebula. What he found changed everything. Andromeda wasn't a nebula within our galaxy, it was another galaxy entirely, containing billions of stars and located 5 million light-years away. The universe had suddenly become unimaginably larger, but Hubble wasn't finished. By 1929, he had made an even more shocking discovery. The universe was expanding. Distant galaxies were racing away from us at speeds proportional to their distance. This wasn't just motion through space. Space itself was stretching, carrying galaxies along like raisins in rising bread dough. The implications hit like a thunderbolt. If the universe was expanding now, it must have been smaller in the past. Trace the expansion backward, and everything converged on a single point at a finite time in the past. The universe, it seemed, had a beginning. This discovery connected modern cosmology back to the ancient creation stories in the most unexpected way. The myths and scriptures that spoke of everything emerging from nothing, of light bursting forth from primordial darkness, of time itself having a beginning, these weren't just primitive fantasies. They were intuitive grasps of a cosmic truth that would take humanity millennia to prove scientifically. But the expanding universe raised new mysteries that were even more profound than the ones it solved. What came before the beginning? What was the universe expanding into? Were the physical laws themselves created at the moment of cosmic birth? Or did they exist in some timeless realm beyond space and time? These questions pushed cosmology beyond astronomy into the deepest waters of philosophy and metaphysics. Scientists found themselves grappling with concepts that mystics and theologians had explored for centuries: the nature of time, the meaning of infinity, the relationship between mind and cosmos, the possibility that reality might be fundamentally different from our everyday experience of it. As our instruments grew more sensitive and our theories more sophisticated, we began to uncover layers of cosmic strangeness that would have been unimaginable to earlier generations. The universe wasn't just larger and older than we had thought. It was weirder, more mysterious, more pregnant with possibilities than any creation story had dared to imagine. The journey from ancient cave paintings to modern cosmology reveals something remarkable about human nature. We are creatures who cannot help but ask the biggest questions. Whether we express our cosmic curiosity through myth or mathematics, through telescope or temple ritual, we are driven to understand our place in the vast scheme of existence. What's changed isn't our sense of wonder, it's our methods of investigation and the scope of what we've discovered. The same impulse that led a Cro-Magnon artist to map the stars on a cave ceiling drives modern astronomers to peer billions of light years into space with the Hubble telescope. The same longing for cosmic meaning that inspired the ancient creation stories motivates contemporary physicists to probe the fundamental nature of space, time, and matter. But here's what all this history has taught us. Every answer reveals new questions, every discovery opens new mysteries, every expansion of knowledge makes the universe seem both more comprehensible and more mysterious than before. We now know that the observable universe contains over 100 billion galaxies, each with billions of stars, many with planets, some possibly harboring life. We've traced cosmic history back to the first fraction of a second after the Big Bang. We've discovered that the universe is not only expanding, but accelerating its expansion, driven by mysterious dark energy that makes up 68% of everything that exists. These are answers our ancestors could never have imagined. But they lead to questions just as profound as any that humans have ever asked. What is the nature of dark matter and dark energy? Are we alone in the cosmos? Is our universe one among many in an infinite multiverse? What is consciousness and how does it fit into the cosmic story? The difference between ancient and modern cosmology isn't that we've stopped wondering, it's that our capacity for wonder has expanded along with our knowledge. We're still those cave painters, still mapping the cosmos, still trying to understand our place in the great mystery of existence. We just have better tools now. And those tools are about to reveal something that will challenge our understanding of cosmic time itself. The entire 13.8 billion year history of the universe, compressed into a single year, showing us just how recent and precious our moment in cosmic history really is. Chapter 7. The Cosmic Calendar. You're standing at the edge of a vast library, one that contains every book ever written about the history of everything. But here's the twist. This library has only one book, and that book has only 365 pages. Each page represents roughly 38 million years. Each day 100,000 years, each hour about 4,000 years. And the entire recorded history of human civilization? It fits in the final sentence of the very last page. This is the cosmic calendar, a way to compress the unimaginable 13.8 billion year history of our universe into something our minds can actually grasp. It's a journey through time that will reveal just how extraordinary and how fleeting our moment in cosmic history really is. Let's begin this journey on January 1st at the stroke of midnight. Not the new year you celebrated, but the birth of time itself. In this single moment, if we can even call it a moment, space, time, matter and energy all spring into existence from nothing. The Big Bang isn't an explosion in space, it's the explosive birth of space itself. For the first few seconds of January 1st, the universe is smaller than an atom but contains everything that will ever exist. The temperature is beyond imagining, trillions of degrees hotter than the core of the sun. In these first moments, the fundamental forces that govern reality separate like streams branching from a mighty river. Gravity splits away first, then the strong nuclear force leaving electromagnetism and the weak nuclear force to dance together a little longer before they too go their separate ways. By 20 minutes past midnight on January 1st, the universe has cooled enough for the first atomic nuclei to form. Hydrogen and helium, the two simplest elements, are forged in this cosmic kitchen. But the universe is still too hot for electrons to stick to these nuclei. It's like trying to form snowflakes in a furnace. For the next 380,000 years in our calendar, that's until late January, the universe remains a glowing fog of particles. Light can't travel far because it keeps bumping into free electrons, like trying to drive through the thickest fog imaginable. But then, as January draws to a close, something magical happens. The universe cools enough for electrons to finally join with nuclei, forming the first complete atoms. Suddenly, the fog clears, light can travel freely for the first time, and the universe becomes transparent. This moment, late January in our cosmic year, is when the universe takes its first baby picture. That ancient light is still traveling through space today, stretched and cooled by billions of years of cosmic expansion. We call it the cosmic microwave background radiation, and it surrounds us like a faint whisper from creation itself. But here's what's remarkable. From February through early September, roughly 8 billion years of cosmic time, the universe remains in what we call the cosmic dark ages. No stars shine because gravity hasn't yet pulled matter together tightly enough to ignite the nuclear fires that power stellar fusion. It's a universe of potential, waiting for the first lights to turn on. September arrives with a bang, literally. Around September 2nd in our cosmic calendar, roughly 400 million years after the Big Bang, the first stars finally ignite. These aren't stars like our Sun, they're monsters, hundreds of times more massive, burning brilliant blue-white and living fast, furious lives that last only a few million years before exploding as supernovas. But what magnificent explosions they are! These stellar deaths scatter the first heavy elements, carbon, oxygen, silicon, iron, throughout space like cosmic seeds. For the first time in universal history, the ingredients for rocky planets and life itself exist. The universe has learned to cook with more than just hydrogen and helium. By mid-September, the second generation of stars begins to form from this enriched material. These stars are more like our Sun, smaller, longer-lived, and capable of nurturing planetary systems for billions of years. Around September 15th, the first galaxies begin to take recognizable shape, their spiral arms traced out by waves of star formation. October marks a crucial transition. The expansion of the universe, which has been slowing down due to gravity's pull, suddenly begins to accelerate. Dark energy, that mysterious force we still don't understand, takes control, pushing space itself apart at an ever-increasing rate. This moment, about 7 billion years ago, determines the ultimate fate of our cosmos. November brings the peak of cosmic star formation. Never before or since will the universe create stars at such a furious pace. Galaxies blaze with the light of billions of newborn suns, and the cosmic web, that vast scaffolding of dark matter, becomes adorned with the most magnificent stellar cities the universe will ever build. But perhaps the most significant date in our cosmic calendar comes on September 1st. On this day, 4.6 billion years ago, a particular cloud of gas and dust in an unremarkable spiral arm of an ordinary galaxy begins to collapse under its own gravity. From this collapse our Sun is born, and around it the swirling disk of leftover materials slowly coalesces into the planets we know today. September 6th marks another milestone, Earth has cooled enough for liquid water to exist on its surface. The stage is set for the most remarkable transformation in cosmic history, the emergence of life from chemistry. The first simple cells appear around September 18th, but for nearly 2 billion years, until November 12th, life remains microscopic and simple. Then, in what we call the Great Oxidation Event, early photosynthetic bacteria begin pumping oxygen into Earth's atmosphere. It's actually a catastrophe for most existing life forms, but it sets the stage for the complex oxygen-breathing life that will follow. As we move through November and into December, the pace of change accelerates dramatically. Complex cells with nuclei appear around November 15th. The first simple multicellular life emerges in early December, but it's not until December 17th that we see the famous Cambrian explosion, that remarkable burst of evolutionary creativity that fills the oceans with an astounding diversity of complex life forms. Life ventures onto land around December 21st, just in time for the holidays. The first forests grow, and the first four-legged animals take their tentative steps on solid ground. December 25th brings the rise of reptiles, including the mighty dinosaurs who will rule the Earth for the next 4 days of our cosmic calendar. But even these seemingly vast stretches of time pale in comparison to what comes next. The asteroid that ends the age of dinosaurs doesn't strike until the morning of December 30th. The mammals that scurry in the shadows finally get their chance to inherit the Earth, but only in the final day and a half of our cosmic year. The first recognizable human ancestors don't appear until 10:30 p.m. on December 31st. Our species, Homo sapiens, emerges just 11 minutes and 46 seconds before midnight. The entire history of recorded human civilization, from the first cities to the pyramids, from the Roman Empire to the Renaissance, from the Industrial Revolution to the space age, all of it happens in the final 25 seconds of the cosmic year. Think about that for a moment. If the universe were a day, human civilization would last less than the time it takes you to say Happy New Year. Jesus lived just 5 seconds ago. Shakespeare wrote his plays 1 second ago. The Declaration of Independence was signed 0.6 seconds ago. The Internet was invented 0.1 seconds ago. This perspective can be humbling, even overwhelming. In the vast sweep of cosmic time, we are newcomers who have barely arrived at the party. But there's another way to look at it that's equally profound. In just those final 25 seconds, we've managed to figure out the entire 13.8 billion year story. We've traced the history of the universe from the Big Bang to the present day. We've discovered that we're made of star stuff, forged in the nuclear furnaces of long-dead suns. Consider the atoms in your body right now. The hydrogen was mostly made in the first few minutes after the Big Bang, January 1st, on our cosmic calendar. The carbon in your cells was forged in the core of a massive star that lived and died long before our solar system was born. The iron in your blood was created in the violent explosion of a supernova. The calcium in your bones was scattered into space by stellar winds from dying stars. You are not just in the universe, you are the universe. You are 13.8 billion years of cosmic evolution made conscious. You are the way the cosmos has evolved to understand itself. But our story doesn't end with this realization. In those final few seconds of the cosmic year, something unprecedented happens. For the first time in the universe's history, matter organizes itself in such a way that it becomes aware of its own cosmic context. Consciousness emerges, and with it, the capacity for wonder, curiosity, and understanding. This isn't just philosophical poetry. It's a fundamental shift in the universe's evolution. For 13.8 billion years, the cosmos evolved unconsciously, following the blind laws of physics and chemistry. Stars were born and died without knowing they were stars. Galaxies collided without understanding their own majesty. But now, in at least one small corner of the universe, matter has awakened to its own existence. We call our current geological epoch the Anthropocene, the age of human influence. In cosmic terms, it began perhaps 0.01 seconds ago, when we first started significantly altering our planet's atmosphere, climate and biosphere. But this influence extends far beyond Earth. We've sent our artifacts to other worlds, our radio signals to other stars, and our eyes and instruments to the edge of the observable universe. In the last fraction of a cosmic second, we've gone from hunting and gathering on the African savanna to splitting atoms and merging black holes in gravitational wave detectors. We've gone from wondering what stars are to understanding stellar evolution better than we understand our own weather. We've gone from being earthbound to having a permanent presence in space. Perhaps most remarkably, we've developed the ability to see ourselves in cosmic context. No other species in Earth's history has ever understood its place in the universe the way we do today. We know our cosmic address: Earth, Solar System, Orion Arm, Milky Way Galaxy, Local Group, Virgo Supercluster, Observable Universe. We know our cosmic heritage. We are the descendants of the first stars, children of exploded suns, carriers of consciousness in a cosmos that spent most of its history unconscious. This awareness brings both privilege and responsibility. We are the universe's way of knowing itself, but we're also perhaps the universe's best hope for protecting the complexity and consciousness that took so long to evolve. In cosmic terms, complex life is both recent and fragile. The conditions that allow for consciousness may be rare and precious beyond measure. As we stand at 11:59 p.m. on December 31st of the cosmic year, we face profound questions about the next second. Will consciousness survive and spread? Will we learn to live sustainably on our cosmic home? Will we find other conscious beings among the stars, or are we the universe's only attempt at self-awareness? The cosmic calendar reminds us that we are both insignificant and extraordinary. Insignificant in the vast scales of space and time that dwarf our brief existence. Extraordinary in our ability to comprehend those scales, to trace our origins back to the first moments of creation, and to contemplate our place in the grand story of cosmic evolution. But perhaps most importantly, the cosmic calendar reveals that we are not separate from this story. We are the story. We are not observers of cosmic evolution. We are cosmic evolution become conscious of itself. We are the universe's autobiography, written in living matter and thinking minds. And this autobiography is still being written. Every discovery we make, every moment of wonder we experience, every act of curiosity and creativity adds new chapters to the universe's story of self-discovery. The cosmic calendar doesn't end at midnight on December 31st. It keeps going, and we are actively writing what comes next. In the next second of cosmic time, roughly the next 38 million years, what will consciousness accomplish? What new chapters will we add to the universe's story? The cosmic calendar reminds us that while our time may be brief, our impact on the universe's self-understanding may be profound and lasting. We are the universe becoming aware of itself, and that awareness has the power to shape what comes next in ways we're only beginning to imagine. The cosmic year is ending, but in a very real sense, the story of conscious cosmic evolution is just beginning. As we contemplate our place in this vast timeline, a sobering question emerges. We've traced the universe's history from its fiery birth to the emergence of consciousness. But what about its future? The cosmic calendar shows us where we've been, but what does it tell us about where we're going? If consciousness appeared just seconds before midnight on the cosmic year, how much time do we have left? And what will happen to the universe and to consciousness itself in the cosmic millennia to come? The answers may be more beautiful and terrible than we ever imagined. Chapter 8. The Fate of Everything. Imagine you could fast forward through time itself, watching the universe age like a flower blooming in reverse, first radiant and full of promise, then slowly wilting, its petals falling one by one into darkness. Right now, at this very moment, you're witnessing the universe at its prime, a cosmic spring where stars are born faster than they die, where galaxies dance in spirals of light, where planets harbour the chemistry of life. But spring doesn't last forever. The universe is writing its own ending, and that story might be more beautiful and terrible than any science fiction ever imagined. We stand at a unique moment in cosmic history. For the past 13.8 billion years, the universe has been growing more complex, more structured, more alive. But the same forces that built everything we see are now conspiring toward a very different future. Tonight, we journey to the end of time itself, to witness the final chapter of the greatest story ever told. The story of everything that exists. 5 billion years from now, our sun will begin its death throes, swelling into a red giant that will swallow Mercury and Venus before finally shedding its outer layers into space. But that's just one star among hundreds of billions. What happens when all the stars begin to die? The universe has been in its star-forming era for nearly 14 billion years, converting hydrogen and helium into the heavier elements that make planets and life possible. But this cosmic alchemy comes at a price. With each fusion reaction, with each stellar birth, the universe uses up its fuel. Hydrogen, the simplest and most abundant element, is being steadily converted into helium, carbon, oxygen and iron. And once it's gone forever. Think of it like a vast forest where trees have been growing for billions of years. At first there seems to be endless space, unlimited resources, but gradually the forest becomes crowded. The biggest trees consume the most nutrients, leaving less for the smaller ones. Eventually the soil becomes depleted and new trees can no longer take root. In cosmic terms, we're approaching that moment of depletion. Star formation in the Milky Way has already slowed dramatically compared to the universe's peak star-forming era 10 billion years ago. The raw materials, vast clouds of hydrogen gas, are becoming increasingly scarce. Computer simulations show us that within 1 trillion years, star formation will essentially cease. The universe will enter what astronomers call the degenerate era, dominated by the cooling remnants of stars that once burned bright. The red dwarfs, those faint, long-lived stars that can burn for trillions of years, will be the last to go. These cosmic lighthouses will shine steadily long after our sun has died, long after the Milky Way has merged with Andromeda, long after human civilization has become a distant memory. But even they cannot burn forever. When the last red dwarf finally exhausts its fuel and fades to black, the universe will have lost something it can never recover: the ability to create new light from within itself. Picture that moment, a cosmos filled with the cold remnants of former glory, white dwarf stars cooling like dying embers, neutron stars spinning in the darkness, black holes growing slowly by consuming the scattered debris of dead civilizations. This is not the heat death yet, but it's the beginning of the end. The moment when the universe's creative phase ends and its long slide toward equilibrium begins. But this stellar twilight raises a haunting question. If all the stars will eventually die, what happens to the galaxies that house them? The answer lies in the invisible force that's been shaping cosmic destiny since the beginning of time. In 1998, two teams of astronomers made a discovery that changed everything we thought we knew about the universe's future. They were studying distant supernovae, stellar explosions so bright they can be seen across billions of light years, to measure how the universe's expansion was slowing down due to gravity. Instead, they found something impossible. The expansion was speeding up. This discovery revealed the existence of dark energy, a mysterious force that comprises about 68% of everything that exists. Unlike gravity, which pulls things together, dark energy pushes space itself apart. And as the universe expands, more dark energy comes into existence, making the expansion accelerate even faster. Imagine blowing up a balloon, but instead of your breath running out, the balloon somehow generates more air as it expands, inflating faster and faster until it's beyond your control. That's what's happening to the fabric of space itself. Right now, dark energy's effects are subtle. Galaxies that are gravitationally bound, like our local group, remain intact. But as billions of years pass, dark energy will grow stronger, while gravity grows weaker due to the increasing distances between objects. Eventually, dark energy will win. The process begins with galaxy clusters breaking apart as dark energy overcomes the gravitational bonds holding them together. Then individual galaxies become isolated islands in an increasingly empty sea of space. The Andromeda Galaxy, currently racing toward us for a collision in 4.5 billion years, will eventually be pushed so far away that its light will redshift beyond the visible spectrum. From Earth's perspective, if Earth still exists, Andromeda will simply fade from view, not because it's dying, but because the space between us is expanding faster than light can travel. This is called the cosmic horizon problem. As dark energy accelerates the expansion, more and more of the universe disappears beyond our ability to observe it. Future civilizations will look up at a night sky containing only the remnants of our local group, a few dozen galaxies in an otherwise empty cosmos. They'll have no way to know that trillions of other galaxies once existed, no way to discover the cosmic microwave background radiation, no way to deduce that the universe began with a Big Bang. They'll inhabit what astronomers call an island universe. Ironically, the same term used to describe our understanding of the cosmos before we knew that other galaxies existed. The future universe will have forgotten its own history, but dark energy's acceleration may have an even more dramatic consequence than cosmic loneliness. If this mysterious force continues to strengthen, it might not stop at simply separating galaxies. It could begin tearing apart the very fabric of reality itself. What if dark energy doesn't remain constant? What if it continues to grow stronger, accelerating the expansion of space at an ever-increasing rate? This scenario, known as the Big Rip, represents one of the most terrifying possibilities for the universe's ultimate fate. The Big Rip isn't just about galaxies drifting apart, it's about the fundamental forces of nature losing their battle against runaway expansion. As dark energy grows more powerful, it begins to overcome not just gravity, but eventually all the forces that hold matter together. The process unfolds like a cosmic unraveling. First, as we've seen, galaxy clusters break apart. Then individual galaxies lose their spiral structure as stars are scattered into the void. But the acceleration doesn't stop there. Eventually, dark energy becomes so dominant that it overcomes the gravitational binding of solar systems. Planets spiral away from their stars into cold, dark isolation. As space continues to expand at an accelerating rate, even smaller structures begin to fail. The Earth itself would be torn away from the Sun, becoming a rogue planet hurtling through empty space. But this is still just the beginning. In the final moments before the Big Rip, the expansion of space becomes so rapid that it overcomes the electromagnetic forces holding atoms together. Molecules break apart. Then atoms themselves disintegrate as electrons are torn away from nuclei. Finally, even atomic nuclei split apart as the strong nuclear force, the most powerful force in nature, succumbs to the relentless expansion of space. The universe ends not with a whimper, but with the complete dissolution of everything that has ever existed. Matter, energy, information, all scattered across an exponentially expanding void, where the very concept of distance loses meaning. Current observations suggest this scenario is unlikely. The strength of dark energy appears to be constant, not increasing. But the possibility cannot be ruled out entirely. If dark energy is driven by something called phantom energy, the Big Rip could occur in as little as 22 billion years from now. Imagine being one of the last conscious beings in such a universe, watching the stars disappear one by one, feeling the very atoms in your body beginning to drift apart. It would be the ultimate cosmic horror story, existence itself coming undone at the seams. But perhaps there's comfort in the fact that the Big Rip, if it occurs at all, is still more than 20 billion years in the future. Our own sun will have died and been forgotten long before space itself begins to tear apart. And there's another possibility entirely, one that suggests the universe might not expand forever after all. What goes up must come down, or so we learned in childhood. Could the same principle apply to the universe itself? For decades after the discovery of cosmic expansion, astronomers wondered whether gravity would eventually halt the outward rush of galaxies and pull everything back together into a cosmic collapse known as the Big Crunch. Picture throwing a ball into the air. If you throw it gently, it rises slowly and falls back to your hand. Throw it harder and it rises higher before gravity wins. But throw it hard enough, at what physicists call the escape velocity, and it will never return. The question is, which scenario describes our universe? The answer depends on the total amount of matter and energy in the cosmos. If there's enough mass, gravity will eventually overcome the expansion, causing the universe to contract back toward a singular point. If there's not enough, the expansion will continue forever. For years, this was one of the great unsolved mysteries in cosmology. Astronomers could see stars and galaxies, but they knew that wasn't nearly enough mass to halt the expansion. Then came the discovery of dark matter, 5 times more abundant than ordinary matter. Suddenly the Big Crunch seemed possible again. But then came dark energy, and with it the realization that the expansion is accelerating, not slowing down. In our current understanding, the Big Crunch appears highly unlikely. But what if we're wrong about dark energy? What if it's not constant, but actually decreases over time? Or what if there are other forms of matter and energy we haven't discovered yet? If gravity were to somehow regain the upper hand, the universe would begin its long journey back toward compression. At first, the reversal would be barely noticeable. Galaxies would slow their recession, pause, and then begin approaching each other again. The cosmic microwave background radiation would start to blue shift, instead of redshift, growing hotter as space contracted. As the universe shrank, galaxy clusters would merge and collide with increasing violence. Stars would be stripped from their galaxies and scattered through space. The night sky would grow brighter as distant galaxies rushed toward each other, their light no longer stretched by expanding space. In the final phase of the Big Crunch, temperatures would soar as matter compressed into an increasingly dense plasma. Stars would evaporate, their constituent atoms merging into a primordial soup of subatomic particles. Black holes would merge into ever larger monsters before finally merging with the contracting universe itself. The end would mirror the beginning, a singularity of infinite density and temperature where the laws of physics break down. Time itself would come to an end or perhaps begin anew if the Big Crunch triggered another Big Bang in an endless cycle of cosmic death and rebirth. It's a poetic ending in a way, the universe returning to its point of origin like a cosmic serpent eating its own tail. But current evidence suggests this dramatic finale is not our fate. Instead, we appear destined for something far more gradual and melancholy, the slow heat death of everything that exists. There's a fundamental law of physics that governs everything from why your coffee gets cold to why the universe will eventually die. It's called the second law of thermodynamics, and it states that entropy, roughly speaking disorder, always increases over time. A hot cup of coffee cools down because heat energy spreads out into the surrounding air. An ice cube melts because the organized structure of frozen water gives way to the random motion of liquid molecules, and the universe itself is slowly running down like a vast cosmic clock that no one can wind up again. This is the concept of heat death. Not a fiery explosion, but the opposite. It's the universe's journey toward maximum entropy, a state where all energy is evenly distributed and no more work can be done. It's like a perfectly still pond where no ripples can form, no waves can carry energy from one place to another. Imagine the universe as a giant mansion with many rooms at different temperatures. Initially, some rooms are blazing hot, like the cores of stars, while others are ice-cold, like the vacuum of space. Energy flows from hot to cold, and that flow powers everything we see. Stellar fusion, planetary weather, chemical reactions, life itself. But eventually, all the rooms reach the same temperature. When that happens, energy can no longer flow, and everything stops. We're already seeing the early stages of this process. The universe today is much cooler than it was shortly after the Big Bang. The cosmic microwave background radiation, once a searing 3,000 degrees Kelvin, has cooled to just 2.7 degrees above absolute zero. Stars convert hydrogen into helium and heavier elements, releasing energy but also decreasing the amount of potential energy available for future fusion reactions. As we saw in our discussion of stellar death, star formation will cease when the universe runs out of hydrogen fuel. Without new stars being born, the cosmos will grow progressively darker and colder. The only sources of energy will be the gradual cooling of white dwarf stars, the spinning down of neutron stars, and the slow evaporation of black holes through Hawking radiation. But here's where the timeline becomes almost incomprehensibly vast. A typical white dwarf star will take longer to cool to the temperature of the cosmic microwave background than the universe has currently existed. We're talking about timescales of quadrillions of years, a 1 followed by 15 zeros. Even more extreme is the evaporation of black holes. Stephen Hawking discovered that black holes aren't perfectly black. They emit radiation and gradually shrink. But the process is incredibly slow. A black hole with the mass of our Sun would take 10 to the 67th power years to evaporate completely. That's a number so large that if you wrote it out, it would contain more digits than there are atoms in the observable universe. During this unimaginably long era, the universe will be a cold, dark place populated mainly by black holes, slowly evaporating into a thin soup of elementary particles. Occasionally, quantum fluctuations might create brief sparks of organization, random atoms assembling into molecules, or even over truly cosmic timescales, the spontaneous formation of complex structures through pure chance. Some physicists speculate that given enough time, and we're talking about periods that make the age of the universe seem like a fleeting moment, quantum tunneling could create Poincare recurrences, where the random motion of particles accidentally recreates organized structures, even entire civilizations. It's a strange kind of immortality. Given infinite time, everything that has ever happened will happen again, an infinite number of times. But this raises profound questions about the nature of time, consciousness, and meaning in a universe approaching maximum entropy. If information is never truly destroyed, what happens to all the thoughts, experiences, and stories that conscious beings have created over cosmic history? In 1961, a physicist named Rolf Landauer made a startling discovery. Information is physical. Every bit of data stored in a computer, every memory in your brain, every arrangement of atoms that carries meaning, exists as a pattern of matter and energy. And if information is physical, then it's subject to the same laws of thermodynamics that govern everything else in the universe. This insight leads to one of the most profound questions about cosmic fate. What happens to information when the universe reaches maximum entropy? If every memory, every thought, every story ever told is ultimately just a pattern of particles, what becomes of meaning itself when those patterns dissolve into cosmic chaos? Consider your own brain right now, holding the information you're learning about the universe's fate. That information exists as connections between neurons, as chemical gradients across cell membranes, as electrical patterns firing through neural networks. When you die, that specific arrangement of matter disperses. The carbon atoms in your neurons might eventually become part of a tree, a rock, or drift through space as cosmic dust. But is the information you carried truly lost? Some physicists argue that information can never be destroyed, only transformed. This principle, called information conservation, suggests that every bit of data that has ever existed continues to exist in some form, even if we can't access it. The information might be scrambled beyond recognition, like a book whose pages have been torn up and scattered to the wind, but the pieces remain. Black holes present the most extreme test of this principle. When matter falls into a black hole, it seems to disappear forever. But Stephen Hawking's discovery that black holes emit radiation created a paradox. If information cannot be destroyed, but black holes eventually evaporate completely, where does the information go? Recent theoretical work suggests that information falling into a black hole becomes encoded on the black hole's surface, its event horizon, in a process called the holographic principle. As the black hole evaporates through Hawking radiation, this information is slowly released back into the universe, though in a form so scrambled as to be effectively irretrievable. This has profound implications for the universe's far future. Even as stars die and galaxies drift apart, even as matter decays and black holes evaporate, the information that once described every star, every planet, every living being might persist in some form. The universe's memory would become distributed across its entire volume, like a vast library whose books have been dissolved into individual letters and scattered everywhere. But here's the haunting question. If information is preserved but becomes completely inaccessible, Does it still have meaning? Is there a difference between information that exists and information that can be read? If the universe retains the memory of every human civilization, every love story, every scientific discovery, but no conscious being can ever access those memories again, are they truly preserved? Some philosophers argue that consciousness itself might be the universe's way of preventing information from becoming meaningless. As long as conscious beings exist to observe, interpret and create new information, the universe maintains its capacity for meaning. But if consciousness is ultimately just another physical process subject to entropy and decay, then meaning itself might be temporary. A brief flame that illuminates the darkness before being extinguished forever. Yet there's another possibility, one that challenges our assumptions about the nature of time and causality. What if the universe doesn't have just one future, but many? What if we live in a cosmos where every possible fate plays out simultaneously? What if the end is also the beginning? Throughout human history, many cultures have imagined time not as a straight line leading from past to future, but as a circle, an eternal cycle of creation, destruction, and rebirth. Modern cosmology has given new life to this ancient intuition through theories that suggest our universe might be just one beat in an infinite cosmic rhythm. The most elegant of these theories is the cyclic universe model, which proposes that the Big Bang wasn't the beginning of everything, but rather the latest in an endless series of cosmic renewals. In this scenario, our universe will eventually stop expanding and begin to contract, ultimately collapsing into a big crunch. But instead of ending in a singularity, the collapse triggers another Big Bang, and the cycle begins anew. Think of it like a cosmic accordion, expanding and contracting in an eternal rhythm. Each cycle lasts perhaps 1 trillion years, long enough for stars to form and die, for galaxies to evolve, for life and consciousness to emerge and contemplate their fate. Then comes the collapse, the rebirth, and the pattern repeats with subtle variations, like a jazz musician playing the same melody with infinite improvisations. This model solves some troubling problems in cosmology. If our universe had a definite beginning, what came before? What caused the Big Bang? The cyclic model sidesteps these questions by suggesting there was no ultimate beginning. The universe has always existed, cycling through phases of expansion and contraction like an eternal heartbeat. But the cyclic universe raises its own profound questions. Does each cycle start completely fresh, with new physical laws and constants? Or does information somehow carry over from one universe to the next? If patterns persist across cosmic rebirths, could consciousness itself be eternal? Not in the sense of individual survival, but as a recurring feature of cosmic evolution. Some versions of the theory suggest that each cycle is slightly different from the last, exploring different possibilities for physical reality. In one cycle, the laws of physics might favour the formation of massive stars and black holes. In another, conditions might be perfect for the emergence of life. Over infinite cycles, every possible universe would eventually emerge, including exact replicas of our own cosmos, complete with identical copies of Earth, humanity, and even you, reading these very words. There's something both comforting and unsettling about this possibility. Comforting because it suggests that nothing is ever truly lost. Every moment of beauty, every act of love, every scientific discovery will recur infinitely. Unsettling because it raises questions about the uniqueness and meaning of our individual experiences. If everything happens infinite times, does any single occurrence matter? Recent observations of dark energy have made the simple cyclic model less likely. For cycles to occur, something must eventually overcome the accelerating expansion and pull the universe back together. Current evidence suggests that dark energy will continue to dominate, leading to eternal expansion rather than cyclical collapse. But physicists have proposed more complex scenarios. Perhaps dark energy itself cycles through different phases, sometimes pushing the universe apart, sometimes allowing gravity to regain control. Or perhaps our universe exists within a higher dimensional space where cycles can occur through mechanisms we don't yet understand. String theory, which attempts to unify all the forces of physics, suggests that our universe might be one of many brains, membrane-like structures floating in a higher dimensional space. Occasionally, these brains might collide, triggering big bangs and creating new universes. In this ekpyrotic model, collisions between brains could cycle endlessly, creating an infinite sequence of universes without requiring our own universe to collapse and rebound. These theories remain highly speculative, but they point to a profound truth. The universe might be far stranger and more resilient than our current understanding suggests. Even if our particular cosmos is destined for heat death, it might be part of a larger system that never truly dies. A cosmic ecosystem where endings are always beginnings in disguise. But perhaps the most remarkable possibility is that consciousness itself might play a role in determining which future unfolds. What if the universe's fate isn't written in stone, but depends on the choices made by the thinking beings who inhabit it? We've journeyed to the far future and seen the possible endings of everything. The slow fade of stellar death, the acceleration of dark energy, the catastrophic unraveling of the Big Rip, the dramatic collapse of the Big Crunch, the gradual descent into heat death, the scrambling of information and meaning, and the possibility of eternal cosmic cycles. Each scenario paints a different picture of ultimate fate, but they all share a common assumption: that the universe evolves according to impersonal physical laws, grinding forward like a vast machine toward predetermined conclusions. But what if that assumption is wrong? What if consciousness, the very capacity for awareness that allowed us to discover these cosmic scenarios, is not just a passive observer of the universe's fate, but an active participant in determining it? What if intelligence, creativity, and choice themselves are fundamental features of reality, as basic as matter and energy? In the next chapter, we'll explore this possibility that consciousness might be the universe's way of transcending the limitations of physics, of creating new possibilities that exist nowhere in the equations of cosmology. We'll ask whether intelligence can ultimately outsmart entropy, whether consciousness can survive the death of stars, and whether the universe might have a purpose that extends beyond the cold calculations of thermodynamics. The universe's fate may not be sealed after all. The same consciousness that allowed us to peer billions of years into the future might also hold the key to changing that future in ways we've barely begun to imagine. The final chapter of the cosmic story may still be waiting to be written, and the authors might be us. Chapter 9. The Conscious Cosmos. Right now, as you listen to these words, something miraculous is happening inside your skull, a 3-pound mass of tissue composed of the same carbon forged in dying stars, the same hydrogen born in the first moments after the Big Bang, is somehow experiencing wonder about its own cosmic origins. This isn't just chemistry, this isn't just biology, this is the universe becoming aware of itself. In 13.8 billion years of cosmic evolution, matter has done something extraordinary. It has organized itself into patterns so complex that they can contemplate their own existence. You are not just in the universe, you are the universe thinking. How do you get from a universe filled with nothing but hydrogen and helium to a being capable of pondering the nature of existence itself? The answer lies in one of the most profound transformations in all of natural history, the emergence of complexity from simplicity. Picture the early universe as a vast, dark ocean containing only the simplest possible ingredients: hydrogen atoms, helium atoms, nothing more. Yet from this cosmic minimalism, through the patient work of physical laws operating across billions of years, emerged galaxies, stars, planets, cells, brains, and ultimately consciousness itself. The story begins with gravity, that gentle architect of the cosmos. In the early universe's nearly uniform sea of gas, tiny density fluctuations became gathering points where matter began to collect. These cosmic seeds grew into the first stars, and those stars became nuclear forges, fusing simple elements into more complex ones. When they died, they scattered their atomic creations across space like cosmic gardeners planting seeds for future complexity. But here's what's remarkable. The universe didn't just create more types of atoms, it created the conditions for those atoms to organize themselves into increasingly sophisticated structures. Carbon atoms began linking with other elements to form molecules. Molecules began interacting to form larger assemblies, and somewhere along this chain of growing complexity, something unprecedented happened. On at least one planet orbiting one star among hundreds of billions, chemistry became biology. Self-replicating molecules emerged that could not only make copies of themselves, but could improve those copies over time. This was evolution's birth, the moment when the universe began actively exploring the space of all possible forms of organization. For billions of years, evolution sculpted living systems of increasing complexity. Simple cells gave rise to complex cells. Individual cells learned to work together in multicellular organisms. And then, in a development that still amazes scientists, some of those organisms developed nervous systems capable of processing information about their environment. Think about what this means. The universe, initially a realm of pure physics, had created within itself biological computers capable of modeling reality. A brain is essentially a three-dimensional map of the world, built from the same atomic materials as stars and planets, but organized in such a way that it can contain representations of stars and planets. And then came the most remarkable step of all. These biological computers became sophisticated enough not just to model their immediate environment, but to contemplate abstract concepts, to ask questions, to seek patterns, to wonder about their own nature and origins. This is emergence in its purest form, the spontaneous appearance of properties and capabilities that were completely unpredictable from the components alone. No single neuron is conscious, yet somehow, when 86 billion of them work together in the precise patterns found in a human brain, consciousness emerges like a flame from kindling. But this raises a profound question. If consciousness emerged so naturally from the universe's tendency toward complexity, how rare or common might such emergence be throughout the cosmos? Are we alone? It's perhaps the most haunting question we can ask about our place in the universe, and behind it lies a deeper puzzle. Is consciousness a natural, inevitable outcome of cosmic evolution, or are we a miraculous accident, the only thinking beings in an otherwise silent cosmos? The rare Earth hypothesis suggests we might indeed be extraordinarily, perhaps uniquely special. According to this view, the emergence of complex life requires such a precise combination of cosmic circumstances that it might happen only once in a galaxy, or perhaps once in the entire observable universe. Consider the astronomical requirements for our existence. We orbit a star of exactly the right size, massive enough to burn steadily for billions of years. but not so massive that it would burn out quickly or flood our planet with deadly radiation. We sit at precisely the right distance from this star, in what astronomers call the Goldilocks zone. Not too hot, not too cold, but just right for liquid water to exist on our surface. But that's just the beginning. Our planet has a large moon that stabilizes our rotation and creates tides that may have been crucial for early life. We have Jupiter acting as a cosmic vacuum cleaner, sweeping up asteroids and comets that might otherwise pummel Earth too frequently for complex life to develop. We exist in a quiet region of our galaxy, away from the radiation-soaked galactic center, but not so far out that we lack the heavy elements necessary for rocky planets. Even our planet's internal structure seems fine-tuned for life. Plate tectonics recycle carbon and regulate our climate. Our magnetic field protects us from cosmic radiation. The list of just right conditions goes on and on, leading some scientists to conclude that Earth-like planets with Earth-like life might be vanishingly rare. But there's another perspective, one that sees consciousness not as a cosmic accident, but as an inevitable flowering of the universe's creative potential. This view points to the sheer scale of the cosmos. With over 2 trillion galaxies in the observable universe, each containing hundreds of billions of stars, many with planetary systems, the raw numbers suggest that even incredibly unlikely events should happen countless times. Recent discoveries have revolutionized our understanding of planetary abundance. We now know that planets are common, perhaps more common than we ever dared imagine. The Kepler Space Telescope alone has identified thousands of exoplanets, and statistical analysis suggests there may be more planets than stars in our galaxy. Many of these worlds exist in their star's habitable zone. Even more intriguingly, we're discovering that life on Earth thrives in environments once thought impossible, around hydrothermal vents in the deep ocean, in acidic hot springs in the most arid deserts, even kilometers underground in solid rock. Life, it seems, is remarkably adaptable and persistent. If it can survive in such extreme conditions on Earth, perhaps it can emerge and thrive in environments throughout the cosmos that we once dismissed as sterile. There's also the time factor. The universe is 13.8 billion years old, and Earth is only 4.5 billion years old. This means there are stars and planetary systems twice as old as our own. If life is common, some civilizations might have had billions of years more than us to develop and spread throughout their regions of space. Consider this: if consciousness is a natural outcome of increasing complexity, then we might expect it to emerge wherever conditions allow sufficient time and energy flow. The same physical laws that created complexity on Earth operate throughout the universe. The same evolutionary pressures that shaped intelligence here should operate on countless other worlds. But this cosmic abundance hypothesis faces its own mystery, one that becomes more puzzling the more we think about it. If the universe should be teeming with intelligence, if consciousness should be emerging on countless worlds across billions of years of cosmic history, then where is everybody? In 1950, the brilliant physicist Enrico Fermi was having lunch with colleagues when the conversation turned to flying saucers and the possibility of extraterrestrial life. After listening quietly, Fermi suddenly asked a question that still haunts us today. Where is everybody? Fermi had done a quick calculation in his head. The Milky Way galaxy is about 10 billion years old and contains hundreds of billions of stars. Even if only a tiny fraction of those stars had planets, and only a tiny fraction of those planets developed life, and only a tiny fraction of those developed intelligence, the numbers were still staggering. There should be millions of technological civilizations in our galaxy alone. Moreover, even traveling at a small fraction of the speed of light, a civilization could colonize the entire galaxy in just a few million years, a blink of an eye in cosmic terms. So where are they? Why haven't we encountered them? Why aren't they here? This is the Fermi paradox, and it's one of the most profound puzzles in all of science. The universe appears perfectly set up for life and intelligence, yet we seem to be alone. The silence is deafening. Scientists have proposed dozens of solutions to this paradox, each more intriguing than the last. Perhaps technological civilizations inevitably destroy themselves before they can spread to the stars. Nuclear weapons, climate change, artificial intelligence or other technologies might create what researchers call great filters, evolutionary bottlenecks that few species survive. Maybe we're looking in the wrong places or in the wrong ways. Advanced civilizations might communicate using technologies we haven't discovered yet. Or they might have moved beyond the need for large-scale engineering projects that we could detect. Perhaps they're deliberately hiding from us, following some kind of cosmic quarantine protocol until we reach a certain level of development. Or consider this possibility. Maybe consciousness is incredibly rare, but when it does emerge, it tends to look inward rather than outward. Perhaps truly advanced civilizations become more interested in exploring inner space, the infinite realms of thought, creativity and virtual reality, than in conquering outer space. There's also the zoo hypothesis, the idea that extraterrestrial civilizations know about us but are deliberately avoiding contact, observing us from a distance like animals in a nature preserve. Or perhaps they exist in such abundance that they've established protocols to prevent interference with developing species like ourselves. But here's a darker possibility. Maybe we're witnessing the great filter in real time. Perhaps the development of technology inevitably leads to self-destruction, and we're seeing the universe in a brief window between the emergence of intelligence and its extinction. The silence we hear might be the echo of countless civilizations that rose to our level of development and then vanished. Yet there's another explanation that's both humbling and oddly comforting. Maybe consciousness is so precious, so difficult to achieve, that we represent something genuinely rare in the cosmos. Maybe Earth isn't just our home. Maybe it's one of the universe's greatest treasures, a place where matter has achieved something extraordinary, the ability to contemplate itself. This possibility makes our existence not less significant, but more so. If consciousness is rare, then every moment of awareness, every act of curiosity, every attempt to understand our place in the cosmos becomes a victory for the universe itself. But whether we're alone or part of a vast community of conscious beings, our search for others has already taught us something profound about the nature of consciousness itself. Since 1960, a small group of scientists has been engaged in one of the most ambitious projects in human history, listening for signals from other worlds. The search for extraterrestrial intelligence, SETI, represents our species' first systematic attempt to answer the question that has haunted us since we first looked up at the stars. Are we alone? The story begins with Frank Drake, a young astronomer who pointed a radio telescope at two nearby stars and listened for artificial signals. He heard nothing but cosmic static, but he had started something profound. Humanity's first attempt to eavesdrop on alien conversations. What Drake and his successors were looking for wasn't little green men in flying saucers, but something far more subtle and potentially more significant, evidence that somewhere else in the universe, matter had organized itself into patterns capable of intentional communication. They were searching for consciousness expressing itself across the void. The search has expanded dramatically since those early days. Today, SETI researchers scan millions of stars across multiple wavelengths, looking for any signal that bears the hallmarks of artificial origin, a pattern too structured, too purposeful to be natural. They listen for the cosmic equivalent of a voice in the wilderness, calling across the darkness. But SETI is more than just a scientific endeavour. It's a profound act of hope and faith. Every hour that radio telescopes spend scanning the sky represents a belief that consciousness is not unique to Earth, that somewhere among the trillions of stars, other minds are wondering about their place in the universe, just as we are. The closest we've come to success was on August 15th, 1977, when astronomer Jerry Ayman detected a strong narrowband radio signal that lasted 72 seconds. He was so excited he wrote "Wow" in the margin of the computer printout. The "Wow" signal had all the characteristics of an artificial transmission, but it was never detected again despite repeated searches of the same region of sky. That single event illustrates both the promise and the challenge of SETI. If we do detect a genuine signal from another civilization, it will likely be a fleeting encounter, a brief moment of contact across the vast spaces and times that separate conscious beings in the universe. But what would finding such a signal actually mean? The discovery of extraterrestrial intelligence would represent the most significant moment in human history, fundamentally changing our understanding of our place in the cosmos. We would no longer be alone. Consciousness would be revealed as a cosmic phenomenon, not a terrestrial accident. Yet even the absence of signals tells us something important. Every star system we examine without detecting artificial signals helps us understand either how rare intelligence is or how different advanced civilizations might be from our expectations. The silence itself is data. SETI also forces us to confront deep questions about the nature of intelligence and communication. What would an alien signal actually look like? How would we recognize a form of communication evolved on another world, shaped by completely different evolutionary pressures and cultural development? Perhaps most profoundly, SETI represents humanity's first attempt to participate in what could be a galaxy-wide community of conscious beings. Every signal we send into space, from our radio broadcasts to deliberate messages like the Arecibo message, makes us part of a potential cosmic conversation. Whether or not we ever hear from others, the search itself has changed us. It has forced us to think about consciousness not as a purely human phenomenon, but as a potential feature of the universe itself, and that leads us to an even deeper question. What exactly is consciousness, and what role might it play in the cosmos? In the early 20th century, quantum physicists made a discovery that would shake the foundations of our understanding of reality. They found that at the smallest scales, particles don't seem to have definite properties until they're observed. An electron doesn't have a specific location until you measure it. A photon doesn't have a definite spin until you check. Before observation, these particles exist in what physicists call superposition, a ghostly state where they're simultaneously in all possible states at once. This is the quantum measurement problem, and it raises one of the most profound questions in all of science. What role does consciousness play in determining the nature of reality itself? The traditional interpretation, known as the Copenhagen interpretation, suggests that the act of measurement, which often involves conscious observation, collapses the quantum wave function and forces reality to choose one specific outcome from all possible outcomes. In other words, Consciousness might not just observe reality, it might actually help create it. Consider the famous thought experiment known as Schrödinger's cat. A cat is placed in a box with a device that has a 50% chance of killing it based on a quantum event. According to quantum mechanics, until someone opens the box and observes the result, the cat exists in a superposition of being both alive and dead simultaneously. It's only when consciousness enters the picture, when someone looks, that reality decides whether the cat lives or dies. This seems absurd, and many physicists have struggled to find alternative explanations. Some propose that measurement doesn't require consciousness. Any interaction with the environment can collapse the wave function. Others suggest that all possible outcomes actually occur, but in parallel universes that we can't access. But what if consciousness really does play a fundamental role in shaping reality? What if the universe remains in a state of quantum uncertainty until conscious beings emerge to observe it and, by observing, help determine its specific configuration? This idea leads to a startling possibility. Perhaps consciousness isn't just a byproduct of cosmic evolution. Perhaps it's a necessary component of reality itself. Maybe the universe requires conscious observers to fully exist, to make the transition from possibility to actuality. Some physicists and philosophers have taken this idea even further. They propose that consciousness might be a fundamental feature of the universe, like mass or electric charge. In this view, every particle, every interaction, every quantum event involves some rudimentary form of experience or awareness. This theory, called panpsychism, suggests that consciousness doesn't emerge from complex arrangements of unconscious matter. Instead, complex consciousness emerges from the combination of billions of simple conscious entities. Your awareness isn't created by your brain. It's what happens when billions of tiny conscious moments combine in the specific pattern that is you. If this is true, then consciousness has been present in the universe from the very beginning. The Big Bang didn't just create matter and energy, it created the potential for experience itself. Every electron, every photon, every fundamental particle carries within it some seed of awareness. This would mean that the history of the universe isn't just the story of matter organizing itself into more complex structures. It's the story of consciousness awakening to itself, growing from simple awareness at the quantum level to the rich, complex consciousness that allows you to contemplate these very ideas. Whether or not consciousness plays a fundamental role in quantum mechanics, there's no doubt that it has transformed the universe in profound ways. Through conscious beings, the universe has developed the ability to study itself, to understand its own laws, to predict its own future. We are the universe's way of knowing itself. But this relationship between consciousness and cosmos raises an ultimate question. If we are the universe becoming aware of itself, what does that mean for our cosmic responsibilities and our ultimate destiny? What if the universe isn't just something that happened to produce consciousness, but something that requires consciousness to fully exist? What if we're not just observers of cosmic evolution, but active participants in the ongoing creation of reality itself? This is the concept of the participatory universe, a profound shift in thinking that suggests consciousness and cosmos are not separate entities, but aspects of a single evolving system. In this view, we don't just live in the universe, we help create it through our observations, our choices, and our understanding. The idea emerges from quantum mechanics, but extends far beyond it. Every time we make a measurement, we're not just recording what exists. We're participating in the process by which reality crystallizes from possibility into actuality. Every act of observation is an act of creation, but participation goes deeper than quantum measurements. Through science, we've become partners with the universe in understanding its own nature. When we discover a new law of physics, we're not just learning about the universe, we're helping the universe understand itself. When we map the cosmic web or trace the history of stellar evolution, we're enabling the cosmos to know its own structure and story. Consider how consciousness has already changed the universe in measurable ways. Through technology, we've begun to redirect asteroids, alter the composition of our atmosphere, and send our signals across interstellar space. We've created artificial intelligences and are developing the capability to modify our own biology. Consciousness hasn't just emerged from the universe, it's becoming a force capable of reshaping the universe. If consciousness continues to evolve and spread, it might eventually transform the cosmos on the largest possible scales. Future conscious beings might learn to manipulate dark energy, engineer new universes, or find ways to prevent the heat death that seems to await all things. Consciousness might literally save the universe from its otherwise inevitable fate. This participation isn't limited to grand cosmic engineering. Every moment of awareness, every act of creativity, every expression of love or wonder adds something genuinely new to the universe. Through consciousness, the cosmos experiences beauty, creates art, asks questions, and seeks meaning. These aren't just pleasant human activities, they're ways the universe explores possibilities that wouldn't exist without conscious beings. The participatory universe also suggests that our search for meaning isn't futile, it's fundamental. When we ask why the universe exists, we're not just curious animals wondering about their environment. We're the universe asking questions about itself. Our search for purpose is the cosmos seeking its own purpose. This creates a profound responsibility. If we're not just products of cosmic evolution but participants in it, then our choices matter on the largest possible scale. How we develop our technology, how we treat other conscious beings, how we explore the cosmos, these decisions don't just affect humanity, they affect the universe's potential for self-understanding and self-transformation. But perhaps most remarkably, the participatory universe suggests that consciousness might be approaching a phase transition as significant as any in cosmic history. Just as the first stars transformed the dark age of the early universe, just as the first living cells revolutionized Earth's biosphere, the emergence and evolution of consciousness might represent the beginning of a new cosmic era. We might be living at the moment when the universe first becomes capable of consciously directing its own evolution. If so, then the questions we're asking about our place in the cosmos, about the nature of consciousness, about our responsibilities to the future, aren't just intellectual exercises. They're the universe's first attempts at conscious self-reflection and purposeful self-transformation. And that leads us to perhaps the most profound question of all. What happens when the universe fully awakens to itself? We began this journey by marveling at the fact that hydrogen atoms forged in the first moments after the Big Bang could organize themselves into patterns capable of wonder. Now we arrive at an even more astounding realization. Those patterns, we conscious beings, might represent the universe's transition from unconscious existence to conscious participation in its own unfolding story. This is not the end of cosmic evolution. It's the beginning of a new chapter. For 13.8 billion years, the universe evolved according to the blind workings of physical law. Matter organized itself into increasing complexity through the patient operation of gravity, nuclear fusion, chemistry and natural selection. But now, for the first time, the universe has produced beings capable of understanding these processes and potentially directing them. Whether we are alone in this cosmic awakening or part of a galaxy-wide community of conscious beings, our emergence represents something unprecedented. The universe becoming aware of itself and beginning to participate consciously in its own evolution. Every question you ask about the cosmos, every moment you spend in wonder at the night sky, every attempt to understand your place in the grand scheme of things, these are not just human activities. They are the universe thinking about itself through you. You are not separate from the cosmos. You are how the cosmos knows itself. And this is just the beginning. If consciousness continues to evolve and spread, if we learn to work with, rather than against, the laws of nature, if we discover ways to communicate with other conscious beings among the stars, then the next chapter of cosmic evolution will be written not by blind physical forces alone, but by the conscious choices of thinking beings. The universe spent 13.8 billion years preparing for this moment, the moment when it could finally ask questions about itself, seek meaning in its own existence, and consciously choose its future path. That moment is now. That consciousness is you. The cosmos is no longer a place where things simply happen to matter. It has become a place where matter happens to think, to wonder, to love, and to dream of possibilities yet unimagined. The greatest adventure in the history of the universe, conscious participation in cosmic evolution, has only just begun. Conclusion. Every ending is also a beginning. Every answer reveals new questions, every discovery opens new mysteries deeper than the ones we thought we'd solved. When Edwin Hubble first realized the universe was expanding, he didn't just solve the mystery of cosmic motion. He revealed that space itself has a history. When we discovered the cosmic microwave background, we didn't just find the afterglow of creation. We learned that the universe once fit in the palm of your hand. When we detected dark energy accelerating expansion, we didn't just uncover a new force. We glimpsed our cosmic destiny written in the motion of distant galaxies. Each breakthrough in our understanding has followed the same pattern that began when the first human looked up at the night sky and wondered. Wonder leads to questions. Questions lead to investigation. Investigation leads to discovery. And discovery leads to even greater wonder. We've travelled tonight from the first moment of time to the end of all things. We've seen how gravity sculpts galaxies, how stars forge the elements of life, how consciousness emerges from complexity. We've glimpsed the possibility that our universe might be one of countless others, each with its own laws, its own story, its own miracles. But perhaps the most extraordinary discovery isn't about black holes or dark matter or quantum mechanics. It's this: in a universe that began as pure energy and simple forces, matter somehow organized itself in such a way that it could think about matter. Chemistry became biology, biology became consciousness, and consciousness became curiosity about everything that exists. You are not an accident in this cosmic story. You are the story becoming aware of itself. The iron in your blood was forged in the heart of an exploding star. The calcium in your bones was created in stellar furnaces that burned billions of years before the Earth existed. The carbon that forms the backbone of your DNA was scattered across space by ancient supernovae and eventually became part of a planet where life could emerge and evolve and wonder about its origins. Every atom in your body is an immigrant from deep space and deep time. You're quite literally made of star stuff, but you are more than the sum of your atoms. You are the universe's way of knowing itself. You are 13.8 billion years of cosmic evolution contemplating its own magnificent story. And that story is still being written. Right now, in laboratories and observatories around the world, humans are pushing the boundaries of knowledge further into the unknown. We're detecting gravitational waves from colliding black holes, capturing images of event horizons, searching for signs of life on distant worlds. Each discovery adds new chapters to our cosmic story and reveals new mysteries that will inspire future generations of explorers. The children alive today may be the first humans to confirm that we are not alone in the universe. They may discover what dark matter really is, or prove that the multiverse exists, or unlock the quantum nature of consciousness itself. They may even find ways to transcend the biological limits that have confined life to single planets orbiting single stars. But whether consciousness spreads throughout the cosmos or remains a rare miracle on a small blue planet, one thing is certain. The capacity for wonder that brought us to this moment of understanding is available to everyone. You don't need a PhD in astrophysics to feel the profound mystery of existence. You don't need a space telescope to experience the awe of looking up at the night sky and realizing you're seeing ancient light from stars that may have died before your species evolved. The universe is not something separate from you that you happen to live in. You are not a stranger here, not an alien visitor to reality. You are the universe expressing itself as a human being for a little while. You are the cosmos experiencing itself subjectively, locally, temporarily, but experiencing itself nonetheless. When you look up at the stars tonight, remember, those points of light are not distant and separate from you. They are your distant relatives. They are part of the same unbroken story that began 13.8 billion years ago with a moment of creation so extraordinary that we're still trying to understand it. The same physical laws that govern the hearts of stars govern the beating of your heart. The same quantum fields that fill the vacuum of space fill every cell in your body. You are not in the universe, you are the universe. You are not confronting a mystery. You are the mystery becoming conscious of itself. You are not searching for meaning in the cosmos. You are the cosmos creating meaning through the miracle of awareness. And so, as our journey through space and time comes to an end, we return to where we began, with wonder. Wonder at the sheer improbability that atoms scattered by ancient supernovae would one day organize themselves into beings capable of reconstructing the history of everything that exists. Wonder at the mysterious forces that transformed a universe of hydrogen and helium into a cosmos rich with complexity, beauty, and consciousness. Wonder at the possibility that this story of cosmic evolution is still in its earliest chapters. The universe is vast beyond imagination, ancient beyond comprehension, and filled with mysteries that may never be fully solved. But it is also intimate, immediate, and present in every breath you take, every thought you think, every moment you spend marveling at existence itself. You are here, you are aware. You are part of something magnificent and mysterious and ongoing, and that is the most extraordinary thing in all the cosmos. The story continues, the wonder never ends. You are the universe, awakening.